All right, can you guys hear me?
Yep.
All right, perfect. So, hi everyone, and welcome to the second Trustworthy AI for Healthcare for AAAI. And we're excited to have you guys here. And let's get started on this workshop. So, AI for healthcare has emerged into a very active research area in the past few years and has made a significant progress. And there are like different AI methods that have achieved human level performance in skin cancer classification, diabetic eye disease detection, chest radiograph diagnosis, and among like other treatments. So while existing results are encouraging, not too many clinical AI solutions are deployed in hospitals or actively utilized by physicians. A major problem is that the existing clinical AI methods are less trustworthy. For example, existing approaches make clinical decisions in a black box way, which renders the decisions difficult to understand and less transparent. So the existing solutions are not robust to small perturbations or potentially adversarial attacks, which raises security and privacy concerns. In addition, existing methods are often biased to specific ethnic groups or subpopulations. These biases may result in unfair predictions that are less reliable for other ethnic groups or other groups. So all these problems render the existing solutions less trustworthy. As a result, physicians are reluctant to use these solutions since clinical decisions are mission critical and have to be made with high trust and reliability. So in this workshop, we aim to address the trustworthy issues of clinical AI solutions, and we aim to bring together researchers in AI, healthcare, medicine, NLP solution, social science, and other areas, and facilitate discussions and collaborations in developing trustworthy AI methods that are reliable and more acceptable to physicians. So we're excited to have 8 brilliant invited speakers. As you can see, we have Professor Carlos Fernandez Granda, we have Professor Magdalena Figueroa-Preston, we have Professor Rada Mihalcha, we have Professor Yuri Shalit, we have Professor Fei Wang, Professor Wei Wang, Professor Jenna Weens, and Professor James Zhu. So in this year, we had around like 40, 60 papers that only like 23 23 of those papers made it to this level and were accepted. So each paper was reviewed by at least 2 reviewers. And in today's workshop, we have 2 programs. One of them is in the morning and another one is in afternoon. So I will put the link for these schedules for both in the chat, so you can just refer to the link. It's on the official website for this program as well. So, and for this workshop, there are 5 organizers: Professor Pentauji, Professor Ranka Zetnik, Professor Byron Wallace, and Professor Eric Jing, and myself. And we're super excited to have these fantastic and awesome talks with you guys. And personally, I'm very excited for the talks. And I know that there are very interesting talks today presenting by different presenters. So we have about like, I think 5-10 minutes till we start the first talk. So please let me know if you have any questions. If not, we can have a short break till Professor Jenna Weens is ready, so we can start the presentation, the first presentation. Thank you. All right, so actually while we're waiting, so I think it would be a good idea to like everyone goes around, like, so there are only like 14 people in this chat, I mean like in this meeting. And so everyone can go ahead and introduce themselves and maybe just a little bit about their background so we can just get to know each other better. So I'll start with myself. So I'm Ramtin. I'm finishing up my third year PhD in UCSD, and I'm working with Professor G, and I'm very excited for this workshop. I'm working on deep learning, machine learning, in both image processing and NLP, related to the healthcare. And I would also suggest, like, if you guys can turn on your videos, so that would be like more, it would be better for the interactions. So thank you.
Thanks, Ramtin. I'm happy to go next. And I'll just echo what Ramtin said in terms of everyone turning on their video, since we're a small group and we're virtual. Normally I'd be able to see all your faces in person. Hopefully we'll get back there soon. I'm Jenna Weens. I'm a faculty member in computer science and engineering at the University of Michigan. I am also the associate director for the artificial intelligence lab here and co-director for Precision Health, a campus-wide initiative here at Michigan, and the first speaker. So you'll hear a lot more about my research in just a few minutes. Carlos?
Hi, everyone. I'm faculty at NYU in mathematics and data science. My group lately mostly does some machine learning for image processing, signal processing, and we have a lot of interest in medical applications. And I'm the second speaker, so you're going to hear much more about my research a bit later on.
Rupali?
Whoever wants to go next.
Yeah, I'll go. Hi, my name is Rupali. I'm a second-year master's student at Mila. I work in healthcare, particularly the rehabilitation of cancer patients. And I have a paper in the second half of the workshop, so please come visit my paper. Thank you.
Hyungu?
Hello, everyone. My name is Hyungu Jung from South Korea. I'm an assistant professor of computer science at the University of Seoul, and I direct a human-centered artificial intelligence lab. And my recent work was focused on developing explainable AI framework, and I'll be very interested in also how to evaluate such a framework as well. I'll be excited to meet with you all here. Right.
Anton?
Hello, everyone. My name is Anton. I'm a second-year PhD student at Chalmers University in Sweden. So I have mostly been working on off-policy evaluation with applications in healthcare. And I have a poster in the first session, so I'm looking forward to meet you there.
Shrajan?
Hi, my name is Shrajan. I am a PhD student at the TU Wien. I work on deep learning applications to extract radiomic features from medical images. I have a paper in the second half of the posters. Looking forward to it.
William?
Hi, everyone. I'm William. I'm a PhD student at the University of Montreal in Mila, and I am currently working on fairness in gaining exchange programs. So I guess I'll be looking forward to discussing with you during the poster presentation.
Who's next? I can't tell who else since no one else has their video on. Would any of the other attendees like to introduce themselves?
Hi, I can go. Let me turn on my camera. Hey, nice to see everyone. My name is Yi Chao Ying. I have a poster session in the first session, and I'm a PhD student at Columbia University here in New York. I'm actually left Columbia, and I'm working in the industry as a senior data scientist right now, starting from this year. So happy to be here. It's a great honor, and happy to see everyone. Welcome to my poster session if you're interested.
Great. Yuri? We're just introducing ourselves briefly. Who would like to introduce themselves next? We've been through everyone except for Yuri.
Hi, everyone. Hi, Jenna. I'm originally from the Technion University in Israel. I work on causal inference machine learning and healthcare. And I'm talking in about an hour. I think I'll give a talk about some of my more kind of applied research in the field. And thanks for inviting me, and happy to be.
Monica?
Hey, thank you. So I'm a first year PhD student with Byron Wallace, was one of the organizers of the workshop, and I work in precision medicine and clinical language processing.
Great. So I think Tareen, Akash, can you, any of you are there and would like to briefly introduce yourselves? Akash, great.
Hi everyone, my name is Akash and I'm a third year PhD student with Carlos, who will be presenting in like second speaker today. And I primarily work in action recognition with an application in stroke rehabilitation. So how stroke patients can rehabilitate and how can we quantify that stroke rehabilitation using action recognition software. So that's what we are focusing on.
Cool, can you?
Hello. I'm Chang Yu-Chen, and I'm a first year PhD student in Illinois Institute of Technology in Chicago, and I'm very interested in trustworthy learning. Yeah. Thank you.
Tareen, if you're there, would you like to introduce yourself? All right, well, maybe we should get started. Ramtin, what do you think?
Yeah, so let me just introduce you first and then you can start with your talk. So our first speaker is Professor Gina Waynes, as I think everyone knows right now. So who will be talking about the augmenting clinical decision-making with AI, incorporating domain knowledge to mitigate shortcuts. So Dr. Waynes is an associate professor of computer science and engineering at the University of Michigan. And her primary research lies at the intersection of machine learning and healthcare. And she received her PhD in 2014 from MIT. In 2015, she was named Forbes 30 Under 30 in science and healthcare. She also received an NSF Career Award in 2016. In 2017, she was named to the MIT Tech Reviewers list of 35 innovators under 35s, among tons of other awards. And Jenna, we're all excited here that you're here, and please take it away.
Thanks, Ramtin. You have to enable host or screen sharing. I can't share my screen. And thank you everyone for turning your videos on and introducing yourself. It's kind of unnerving giving a talk to like completely dark screens with no interaction. So it's nice to see some faces and the global representation that we have. It sounds like we're spanning multiple time zones here. All right. Yep, it works now. So there we go. All right, so this is a quick 25-minute talk on our work, really just a sliver of our work on incorporating domain knowledge to mitigate shortcuts. So in hospitals today, we're collecting just an immense amount of patient data. And in my research group, Machine Learning for Data-Driven Decisions, we develop and we use machine learning techniques to detect patterns in these data, patterns that can be used to sort patients from low risk to high risk for a particular adverse outcome or bad event, or match patients to appropriate treatment with the ultimate goal of augmenting clinical practice and improving patient care. And today I'm really going to focus on our work on patient risk stratification and diagnosis. But if you're interested in learning more about our work in selecting treatments and reinforcement learning for healthcare, you can check out the papers that we've published recently in this area, or even a talk that I gave yesterday at another AAAI workshop on AI for behavior change. So given the challenges that today's healthcare system is facing, there's a critical need for these sorts of clinical decision support systems. Currently, the demand for clinical care far exceeds the supply, and economists anticipated this was only going to get worse even prior to the pandemic. They had estimated that we would have a shortfall of over 100,000 physicians in the US by the year 2030. And this shortage exacerbates what's already a serious issue in the field, clinician burnout. At this point, I hear all the time that the increasing computerization of the field of medicine is more of a problem than a solution, because clinicians are spending more and more time entering and studying data about their patients while still ignoring the vast majority of it. And this burnout, combined with a lack of tools to make sense of all the data, has contributed to a large number of medical errors. So a study that was published in the British Medical Journal back in 2016 estimated medical errors as the third most common cause of death in the US after heart disease and cancer. And to put this in perspective, in the US in 2021, there were approximately 450,000 deaths involving COVID-19. So these issues highlight an important need, but also an opportunity for AI to help alleviate some of these issues. But before I get into some of the methodology behind our approaches, I want to tell you a story. So early on in the pandemic in March 2020, Michigan Medicine, like hospitals around the country, was worried about running out of space, running out of beds. So members of the AI lab, including myself and my students, partners with researchers at the hospital here in Michigan to develop patient risk stratification tools, tools that could identify which patients with COVID-19 would develop severe illness or die in the hospital to help with resource management. And the work was recently published in the British Medical Journal, but the final model was not the initial model. So early on, we worked with data-driven feature selection techniques to identify a small list of relevant factors for making this prediction, who was going to develop severe illness or die in the hospital. And one of the features that came up was this lab result, hematocrit, as being predictive. It was a risk factor for developing severe illness. And hematocrit is a measure of the proportion of red blood cells in the blood. And while we didn't know much about the disease at the time, the clinicians were left puzzled as to what the physiological connection might be between this particular lab result and the disease. Well, with a little bit of digging and talking to clinical informaticists specifically about hospital workflows, we learned that hematocrit can be measured in a few different ways. It can often be measured using a complete blood count. Here, this particular lab test was a special way of measuring hematocrit using arterial blood gas. And these typically only routinely are collected in the pediatric hospital, not at the adult main hospital. And so it so happened that our regional infectious containment unit, or RICU, was in the children's hospital at the time. Michigan set one up in early 2020. And initially, the hospital placed some of the sickest patients in this location in the RICU. But later the unit was closed when the surge subsided. So this was not a robust feature. It was a proxy for location, which was spuriously correlated with the outcome. In other words, it was a shortcut. And this is really the problem with AI across many domains. It can pick up on spurious correlations. So for example, if you have a model that you're training on images to recognize cows, it can fail if the cow shows up in an unexpected place, because instead of learning what makes a cow, the model ends up relying on a shortcut that is the green background in this case. And while this might not harm any cows, it presents a really serious issue in healthcare, since models can perpetuate or even exacerbate human biases in clinical care. And at the root of the problem is the fact that models lack common sense. We design them to optimize some objective function, even if that means relying on shortcuts. They will optimize. So in our work, we aim to address this lack of common sense with clinical knowledge. And people often talk about augmenting clinicians with AI, but it works both ways. Clinicians can also help augment models. We know that models are error prone, and moreover, rarely can they capture all of the nuances of a clinical situation. So in our work, we're really aiming to augment the models with clinical expertise. So in today's talk, I'm going to describe briefly two projects along these lines. So the first presents an approach for incorporating expert knowledge through a regularization penalty, while the second leverages a related task informed by an expert to mitigate shortcuts. So let's start with the first idea, the first project, in which we're going to consider, just to ground this, the task of predicting who is likely to develop an infection during their hospital visit. And we're going to rely here on tabular data extracted from the electronic health record. And in my group, we've been training models to predict these sorts of healthcare associated infections for some time now. And we're frequently asked, well, what are the most important features? And when using a linear model, we can look at the learned parameters or sort features by their model coefficients and investigate which features are contributing most to the prediction. And we see things that are reassuring, like an infection in the past year is predictive of having an infection in the current hospital visit. Being in an intensive care unit is also predictive. But we don't have to get too far down the list before we start to see some weird things, like the fact that vitamin B is associated with risk. And something like vitamin B can end up showing up simply because it's highly correlated with another risk factor that was eliminated during training. And this can lead to a lack of robustness when applied prospectively, especially if clinical protocol changes. So though the model lacks common sense, clinicians have a great deal of it. So knowing that there are some factors that are associated with increased risk of infection, we sought to develop methods that could incorporate this knowledge without harming model performance. And in high dimensional settings like our own, to decrease the size of the rule set. So we're training these models, we're minimizing some loss function subject to some regularization penalty. And oftentimes what we see are people relying on things like the lasso or L1 because it encourages sparsity in the set of parameters. And this makes it an attractive choice if you want to reduce the set of features that are important to the model prediction, but it can end up but randomly eliminating a feature. If you have two perfectly correlated features, your solution will lie along this line. So if X1 and X2 are perfectly correlated, your solution will lie along this line, 45-degree line. And then given the constraint, you could end up at either this corner or this corner, actually anywhere along here. And L2 will give similar weights to both. So you won't end up with that sparsity necessarily that you get with L1. And this is the problem with lasso is that you can end up incorporating the sparsely correlated feature instead of the one that actually matters, that clinicians know matter. So to incorporate expert knowledge regarding what is known to cause an increase in patient risk in the form of a new, we do this in the form of a new regularization term. So for every input variable, so we have D input variables, we include an additional binary flag, okay, R, that tells us whether or not that feature is known to be associated with increased risk or not. And we assume that there's some subset of the features that the expert believes to be important. And the others are just set to 0. They could be important, they could not, we don't know, right? That's why we need data-driven approaches. So this results in 2 sets of parameters, those that correspond to the features that are known in K and those that are unknown, not in K. And this regularization penalty that we've developed here, I'm showing you the equation and then I'm showing you the contour plot right here, takes this information into account when deciding between 2 correlated features. So now the solution is going to set the parameter or the model coefficient of the unknown feature to 0 and set a non-zero weight for the known. And we call this regularization penalty the I penalty, just based on its shape. And the penalty exhibits a number of nice properties, which we lay out in the KDD paper. So first, it's a norm, which ensures that it's homogeneous. And next, as you can see from the equation, depending on how I set R, it's a generalization of lasso, ridge, and elastic net. And finally, and perhaps most importantly, I favors a solution that is sparse in the set of unknown correlated features. So I get that sparsity, but dense in the set of known correlated features. So we end up with this density here and this sparsity here where we're applying L1. So applied to the task of predicting healthcare associated infections, we worked with experts in infectious disease to comb through the literature and identify, well, what were the most important known risk factors? Things like receipt of antimicrobials, things like previous diagnosis of infection, and we trained a model that relied on just those features. Okay, this was the expert features only model. And that model didn't do very well in terms of the area under the curve. It achieved an area under the curve just above random of nearly 0.6. We also looked at this measure of average precision, which essentially measures how often the known risk factors appear near the top of the ranked list. And the expert features only trivially achieve an average precision of 1 because it's only relying on the expert features. So they're all going to appear near the top of the list. In comparison, the I penalty has a lower average precision. So some of the unknown features end up being important and trickle up to the top of the list. But the discriminative performance of the model improves. And compared to other common regularization techniques, and we compared to a number of others in the paper as well, but just here, lasso, weighted lasso that takes into account this information, R, it has this additional information, and elastic net, we achieve similar discriminative performance, but significantly higher average precision. We're really choosing, when we have these correlated features, the one that clinicians think matters. And one of the things you might be wondering is, well, what if the clinician's wrong? That can happen. So to experiment with this idea, we took the R vector, remember that's our D-dimensional vector that's encoding what matters and what doesn't, or what clinicians think matter and what doesn't, and we randomly permuted it. And this essentially corresponds to garbage expert knowledge. And what was really interesting here is that we're not encouraging the model so much that it's resulting in a huge drop in the AURC. So we see a small decrease in the AURC and a much bigger drop in the average precision. So if the data doesn't agree with the clinicians, this is actually a feature of the model. This can highlight that. So takeaways for this part. We developed a regularization technique that incorporates expert knowledge about what the expert believes to be important and unimportant to help select among perfectly correlated features. And we showed that this penalty is a generalization of existing regularization penalties. If you want to start training models today, with the I penalty, you can check out the paper that was published a few years ago in KVD and our code on GitHub. And I just want to highlight the two students who worked on this project, Joshua Wang and Jihei Oh. Okay, so moving on to the second part of the talk, we're going to shift gears and we're going to focus on a different clinical task in part so that we can look at a different modality of data. So the first part of the talk, we were looking at tabular data from electronic health records and linear models. Here, we're going to focus on chest x-rays or imaging data collected in healthcare. And the goal is to make a diagnosis based on this type of data. And specifically, we're going to consider the problem of diagnosing patients who present in the emergency department with acute respiratory failure. And there are several underlying causes, but the most common causes include heart failure, pneumonia, and chronic obstructive pulmonary disorder, or COPD. And this is a really challenging clinical problem. In up to 30% of cases, patients receive incorrect initial treatments. So clinicians don't get it right away every time, and that can lead, the misdiagnosis and incorrect treatment can lead to harm. So tools that could help clinicians in making this diagnosis could ultimately improve outcomes. So we looked at using deep learning applied to chest x-rays to estimate the probability of pneumonia, COPD, and CHF. And here the probabilities don't sum to 1 because these are not mutually exclusive. You can have any combination of these underlying etiologies. So our study cohort consisted of nearly 1,300 patients admitted to Michigan between 2017 and 2018. And included those who developed acute respiratory failure. And then to get the ground truth diagnosis, each patient was independently reviewed. So we did chart review by at least 2 physicians and assessed on a scale of 1 to 4. And then we averaged and thresholded those scores to get our labels, our binary labels for COPD, CHF, and pneumonia. So in the context of learning to diagnose based on chest x-rays, when we first started the project, we were getting really good results. And when we started to look at, well, what had the model learned by looking at some of the activation plots, they looked weird. So we presented them to our collaborators, a pulmonologist and a radiologist. And they said, no, the model's not looking at the right things. It's looking at things like bone structure and breast tissue. And this is a problem. And the model was essentially picking up on spurious correlations. There was this high skew in the training data between the sex of the patient and the outcome of the patient. So it was just learning to identify who was female or not. So we took this a step further and we wanted to see, well, what other shortcuts could a model learn to exploit? And how easy is it to exploit, in particular, sensitive attributes like sex and race and age? So first we asked, well, how easy is it to learn whether or not someone is female? And in the Michigan data, remember, we had only 1,300 images or patients, and we had to split that into train, validation, test. So a really tiny training set compared to a lot of computer vision tasks. We were able to achieve a near perfect AUROC, near perfect discriminant performance with respect to predicting whether or not the patient was female. And we repeated this on the MIMIC cohort and the Chexpert cohort, much bigger cohorts from Beth Israel Deaconess Medical Center in Stanford. And I've never seen 95% confidence intervals like this before, but it was trivial for the model to predict sex. And we found that the model could also get signal, relatively good signal, with predicting other sensitive attributes like age, body mass index, and even race. And this really creates a problem when you're transferring across institutions. Like Michigan is just down the road from the Veterans Affairs Hospital, which is mostly male patients. So when demographics shift, the models might no longer work. And the potential of shortcuts related to sensitive attributes could also lead to bias amplification, in which human biases are not just replicated, but actually amplified by the model. And this is all to do with sensitive attributes. And that's very worrisome. But there are other sources of shortcuts that can be detrimental when it comes to model performance that don't have anything to do with demographics. And I want you to consider these two images. So 2 chest x-rays taken from the same individual, except for one small difference. Can anyone tell what that difference is? Let me pull up your pictures here. You're all squinting. Rupali, you're smiling. Do you know what it is?
Nope, I'm usually good at these tasks, but I'm surprised that I can't find it.
Yeah, well, I've given this talk a few times now, and we're all looking at this in different screens, right? Different lighting conditions, so it can be hard. Both images are processed using a Gaussian filter, but the one on the left, the Gaussian filter has a standard deviation of 0.4, and the one on the right has a standard deviation of 0.5. Okay. To date, no one in the audience has been able to identify that difference, but a model can do this with near perfect accuracy. It's trivial for a model to separate these two, and that presents a serious issue because we have these data sets floating around, right? The MIMIC data set, the Chexpert data set. We don't always report all of the pre-processing that's been done before making these data available. And if the distribution of outcomes is different in different across these different data sets, we might just be learning, once we pull them together, differences in pre-processing, which is really concerning. All right, so quickly recognizing the potential of deep learning approaches to exploit shortcuts, we investigated approaches to mitigate such behavior. And in particular, we looked at a simple transfer learning approach. So why are we interested in transfer learning? Well, we want to encourage the model to rely on clinically relevant features. So very similar idea to the first part of the talk. And we know that clinically relevant features are more likely to generalize across tasks. So we were inspired by the way in which clinicians will reuse common radiological findings when diagnosing disease. So in our setup, we have some target tasks that we aim to solve. So we want to identify whether or not the patient has congestive heart failure, but we have only a very small, potentially very biased, I think 1-to-1 correlation. And if we only leverage the training set, we will almost certainly learn shortcuts and will fail to generalize. So we assume access to some related but curated source task that share similar features. So here we're going to consider a source task in which we're trying to diagnose pneumonia. We have a very simple transfer learning approach where we first learn the model. Here's just a dense net. We have our encoder, E, and then our linear layer. And essentially, we're going to freeze everything except for that last layer. And we're going to fine tune this last layer on the target task. which remember is highly skewed. So though this is a really simple approach, it proves surprisingly effective. So assuming that the target task was predicting congestive heart failure and the source task was pneumonia, and we had a strong correlation, so a correlation of 1, between age being greater than 65 and the outcome. Without any transfer, we did not do very well on the task. But with the transfer learning approach, we can recover substantially. And we showed that this result held across other types of sensitive attributes, including even things like pacemakers. So I will, all the code, I wanted to point to the code, all the code's available. Again, on our labs, we have both a GitLab and a GitHub. They're just mirrored, so you can find the code either place. I want to highlight the student who led this work, Sarah Jabour. If you want to find out more, you can check out the paper MLHC 2020. Our clinical collaborators, Dr. Michael Schoding and Dr. Ella Kazaruni, and my colleague here in computer science and engineering and expert in computer vision, David Foey. But we didn't stop there. Based on this work, we conducted a pilot study in which we showed clinicians a clinical vignette, okay, like the one here, and asked them to diagnose this patient. So do you think it's likely or unlikely that they have pneumonia? Or pneumonia, heart failure, or COPD. And in the pilot study, we found that clinicians were around 70% accurate, which is what we expected. It's a difficult clinical task. When we gave them the output of an AI tool, their accuracy increased. But when we gave them a biased AI tool, their performance tanked. And similar results were reported last year by Goeb et al. And they were able to show that clinicians could, to a certain extent, identify inaccurate advice rating at lower quality. We're interested in to what extent can we equip clinicians with tools that they can recover from this bad advice. So do these sorts of explanations or activation maps help? So that's what we're working on now, along with other collaborators in human-computer interaction and critical medicine. All right, so takeaways here. Deep learning models can classify demographics, treatment, image preprocessing based on a chest X-ray alone. We should be concerned, but transfer learning is surprisingly effective at mitigating shortcuts, but it's not the be-all and end-all solution. I think we're going to need a combination of both human-based and computational-based strategies to make sure that these models are robust. So I will end there so that we have time for questions and open it up. Thank you. Are there questions?
I think there is one question from Yuri in the chat. So
great.
Actually, I wrote something on the chat, but I have a question that I think might be more interesting.
Sure.
And thank you for the great talk. And I'd love to hear your thoughts about it. So shortcuts, in my experience, they're not clear cut, right? If something is kind of stable in one health system, maybe, right? In the Michigan, area, maybe it's okay to use it, right, in your own system, but you won't transfer it to, to a different country. So how do you think about this kind of spectrum of shortcutness?
Yeah, I love that question. And we could spend the next 30 minutes talking about it. I have a lot of thoughts. I think my short answer is it depends, right? I think that there's a time and a place for what we'll call boutique machine learning, right? Machine learning for your institution, for your hospital, for your patients. But you have to be careful because clinical workflows can still change, right? So even in Michigan medicine, like the shortcut related to the Regional Infectious Containment Unit, the RICU, that opened, it got shut down a few months later. If we had deployed that model, the performance would have suffered. And that's, in fact, I think there was an article by Casey Green and others, or Casey Ross and others in STAT yesterday about the degradation of a model to predict sepsis over time and just mimic. So I think that you can, to a certain extent, rely on models, shortcuts, so long as they persist. over time within an institution. And you can check that. Now we have, a decade of data at Michigan. So to a certain extent, we can measure this robustness to features. But then there are other times where you want a model that really generalizes. So in the COVID-19 work that we did, we wanted a model that worked not just at Michigan, but could work at other institutions. So there we really shrunk the set of variables down. Typically we have hundreds, if not thousands of variables. That model had 9. It had 9 variables that we could be more confident would actually generalize because they had some physiological mechanism that clinicians could explain, or were a proxy that clinicians think would hold in other institutions. And then you really have to do validation. So we went and we validated that model at 12 external hospital centers. We validated at 12 external hospital centers. We validated across different race and ethnicities, across age groups, and across time to check robustness across all those dimensions. But yeah, I think it depends on the application and the use case. About whether or not it's okay to rely on things that would be a shortcut or would not generalize externally.
Thank you. I love the term boutique ML.
If any of you have follow-up questions, feel free to reach out to me either in the chat or over email. I don't want to take up the next speaker's time. Thank you.
Thank you so much, Jenna. So thanks for the great talk. So I think there's one more question. Maybe we can take this one.
Please. Yeah. Do we have time for more questions?
Just, if you make it quick,
Okay, quickly. Okay, I actually had 2 questions. Question number 1, in the first task that you had explained, if you remember, there was one where the AP, the average precision was 1, but the area under the curve was like 0.5 something. Like, I didn't understand why that was low as compared to like the other machine learning methods. And if you don't mind, I'm gonna ask the second question as well, if you have time to answer that. So my second question is, in the transfer learning experiment, I'm not sure that I understood it completely. So there was one experiment and then you did transfer learning on another task. And then it was performing really well on that as well. I didn't understand why it was performing well. Was it because the image quality on the first task was better or something? Like, I didn't understand why it was performing well.
So to answer your first question, the model that was based on expert features only did poorly because it didn't account for all the other unknown important risk factors, right? So clinicians know a lot, but they don't know everything. And the other models were able to incorporate that. I'll take your second question offline. Maybe we can chat during the break because I think we are over and I don't want to take up too much of Carlos's time. Thanks, Rupali.
Great, thank you.
Thank you so much. So our next speaker is Professor Carlos Fernandez-Grande, who will be talking about deep probability estimation. And Dr. Fernandez is an associate professor of mathematics and data science at New York State University. His research focuses on the design and analysis of data science methodology. Currently, the main focus of his group is machine learning and the application to the medicine, climate science, and scientific imaging. And Carlos, we're excited that you're here, so please take it away.
Let me unmute myself, that should be useful. Please interrupt me at any point and I'll be asking questions as I go along because we're not that many, so let's try to make this a little bit more interactive. Today I'm going to talk about deep probability estimation. I want to acknowledge that this is partially supported by NSF and NIH, and this work was done by my students. It was really a team effort in my group. So I want to highlight these are mainly my students and my postdoc Matan, who are the ones that really did the work. So, and 2 of them are joining us here. Okay, so we're going to take a look at the problem of estimating probabilities of uncertain events from high-dimensional inputs. These high-dimensional inputs will be images or videos, but you could imagine applying it to other high-dimensional, even multimodal data. I want to emphasize to start with, because this has been problematic when I've explained this stuff in the past, that we're not looking at classification because we're interested in events that have inherent uncertainty. And I think this will become clear when I tell you some of the examples that we worked with, one of which is in healthcare, but the others are not. So the first one, which is very typical for uncertain events, is weather forecasting. So we want to know, will it rain? Will it snow? What temperature will there be? And what we have is input in this case, for the data set that we actually used here, we have maps of past precipitation. So we know, what precipitation there was in a certain area maybe an hour ago. We want to know what's the probability that it will rain an hour later. So clearly it's not classification because it could rain or not, given the exact same map. Given the exact same input, there is an inherent uncertainty about the outcome. Okay. Another application which is not in healthcare is collision prediction. So your self-driving cars, you want to know if there's going to be a car crash in, let's say, 10 seconds. We use the data from this paper. I really want to acknowledge that, where basically you have short videos, and then you have to predict whether there's going to be a crash or not. In this case, it's not looking great. Again, there's inherent uncertainty because there could be a certain situation, and due to the skill of the driver or some other factors that are not reflected in the input, there could be a crash or not. This is about outputting probabilities. And finally, healthcare. This is really connected to survival analysis. Here we're going to not talk about survival analysis in the sense of how long is it going to be until a certain patient dies, but rather as a probability estimation problem, where we say we set a certain time and we say, well, will a cancer patient, for example, die in the next 5 years? And the input would be the histopathology slide showing you tissue, cancerous tissue from the patient. Okay, again, there are many other factors beyond what is captured in the tissue that would determine whether the patient would survive or not. So what we want is a probability. Is everyone fine with the setup? We have high-dimensional inputs, images, videos, and we want to estimate probabilities of an event of interest. Any questions up to here? Okay, so we're going to do this with deep learning because of the fact that we have high-dimensional inputs, and as many of you probably know, deep neural networks are very good at processing high-dimensional inputs, often in mysterious ways, but they're just really good. So our goal is to have a trained neural network where we would input our high-dimensional input, and we would get a good probability of the event that we're interested in. I'll get to what a good probability means in a moment. I want to emphasize that when you look at the data that you have to train this kind of models, you do not have the probability that you're actually interested in estimating. Okay, you only have past data where you know whether it rained or not. You know whether there was a car crash or not. You know whether the patient survived or not. So we don't get to see this PI. We get to see YI, which we assume is sampled from this true probability, but we only get to see the sample. If you want, we only get to see zeros or ones. We don't get to see the probability that we're really interested in during training. Okay, does that make sense to everyone? And that's what we have to train these networks. All right, so let's go to the question of how to evaluate whether these estimated probabilities are good. A reasonable thing to ask is they should be well calibrated. What do I mean by well calibrated? I mean that if I take all the estimates for which I said that the estimated probability, all the inputs, sorry, for which I said that the estimated probability is 0.7, ideally 70% of those should be 1. 70% of those should be rain or collisions or death in the case of survival prediction. Okay, that if that's the case, then we say that the model is well calibrated. The way we do this in practice is we bin the points, the examples, according to their estimated probability, and then we looked at the empirical probability within those bins. Sorry, I got ahead of myself. And then we check, okay? I will show you some diagrams later on that show exactly this. Maybe that will make it clearer. So now I have a question. Is calibration enough? Okay, if a model is well calibrated, can we be happy and go home? So in order to see whether that's the case or not, let's take a look at a very simple example. So imagine you have two kinds of patients that are very likely to die, patients that are not very likely to die, okay, in 5 years. Unfortunately, we will all die eventually. So some of them have 1/4 and some of them have 3/4. This is obviously a very good model because what happens is that the model, and by the way, this is a 1. Actually, I should have made that very clear. This is a 1, this is a 0, this is a 0, this is a 0. Okay, and the same for the red class. This is a 1, this is a 0, 1, 1. Okay, so we train our model and we get this output. We're very happy. What has happened? The model has said that these guys all have probability 1/4, and these guys have probability 3/4. Is the model well calibrated? Where we go and we see the empirical probability here. There's 1/1 out of 4 examples. Yes, 1/4. Excellent. Here we take a look. 3 out of 4. Excellent. Good calibration. Now let's take a look at another case where we train our model and our model says like, you know what? The probability of everyone is actually 0.5. I think that's the probability of everyone. So what do you think? Do you think this is well calibrated or this is not well calibrated? So to see whether it's well calibrated or not, what do we need to do? We need to look at the empirical probability. And there's 4 1s out of 8 points. So this model is perfectly calibrated. And there you can see the difficulty in evaluating probability estimation, because it's actually very easy to produce a very well calibrated probability. I look at what is the probability of rain in general, and I say, oh, that's the probability always. That's actually going to be a well calibrated estimate, but it's completely useless. Okay, I see how often there's a car crash. I say, okay, that's the probability. That's it, I'm done. Again, useless because I'm not even using the input, right? We want very discriminative, if that makes sense, probability estimates based on the input that we give to these networks. I'm not going to get that into detail, but in practice, a good way of evaluating whether a probability estimate is discriminative is the Breer score, or you can look at AUC combined with a calibration metric. If you just look at AUC, you might be very uncalibrated, but if you combine it with a calibration metric, that's a reasonable way to check these things in practice. Here, we're going to take a look at a simulated data set that we created precisely to at least have a controlled situation where we can look at what happens with probability estimation. Okay, the data set is face-based risk prediction. So the idea is the input is the face of a person, and we need to predict the probability that they contract a certain disease. This is simulated. So what we did is we use the age of the person to assign them a risk. In this case, we have several different ways of doing this because we wanted to explore the different factors that affect probability estimation. For this example that I'm showing you, we just divided by 100. Okay, so this person is age 20. The probability of contracting the disease is 0.2. When we're training our models, we will only see whether the person contracted the disease or not. In this case, they were lucky, they didn't contract the disease. This is another example, an older person who is 70. The probability is 0.7. They were unlucky, they contracted the disease. Okay, and the game is to predict the risks of new people in our test set using a neural network that is trained on this training data where we just get to see the faces and the labels. And I want to acknowledge that we use data from this paper where they released this data set where we had the faces and the ages to produce this synthetic data set. Okay, so how do we train our models to perform probability estimation? It turns out that if you do standard cross entropy, like if you minimize a cross entropy loss exactly like when you just train something to do classification, when you train a model to do classification, that actually, if you look at the theory, if you want, that should work. Why? it turns out that the standard cross entropy loss is a proper scoring rule. So if you get to see the whole distribution of the data and you minimize cross entropy, it's going to be well calibrated. But the important thing here is I'm seeing the whole distribution of the data. So this would mean that when you train your model has access to infinite data. To show you that this is actually true, we simulated an infinite data regime where at each epoch, we resampled whether people were ill or not. So now I told you like this person got the disease, this person didn't. To simulate the infinite data regime, we continuously sampled at each epoch whether they were ill or not. Okay, and we trained the model like that. So the model didn't really have access to infinite data because it's always the same phases, but at least to many, many different possible outcomes, so it could learn the probability. So if we do that, these are the results that we get. This is so I'm plotting here the true probabilities because in our synthetic data set, we know them against the estimated probabilities, and the model actually works very well. Below, I'm going to draw like I'm going to show you a reliability diagram, which is what you would plot in practice, where you would do this thing where you bin your predicted probabilities, and then you see what's the actual empirical probability there, for points where you predicted between 0 and 0.1, between 0.1 and 0.2, and so on. And you see whether they correspond to the observed frequencies in the test set. And when this infinite data regime, this is perfect. Okay, like it works very well. Of course, there's a certain uncertainty because it's not so easy to predict the age and hence predict the risk. And some people look older, some people look younger as well. All right, so what do you think is going to happen if we train this on the actual data set where we fix whether each person is ill or not, and we train for a long time? Can someone tell me what will happen?
I have a question here, if that's
Sure.
okay. So in the infinite data, the graph on the top left, so I see that the predicted the graph is leaning more towards the left. So does that mean that the predicted probability is sometimes lower more often lower than the ground truth probability? So that means that the predicted probability is more conservative as compared to the ground truth probability?
That's correct, and you can also see it here.
Okay.
Yeah, that's correct.
Thanks.
So, okay, my question is, now no infinite data anymore. We have our data set, which is what happens in the real world. We train this thing, and I train it for a long time. What is going to happen? And it has to do with neural networks and how powerful they are. Anyone want to venture a guess?
Overconfidence.
So overconfidence, or to put it in another way, you will learn the zeros and ones. The neural network will be able to tell apart, right? Like you will be able to tell apart so you can see here the zeros and ones, okay? So this is on test data actually. So you get overconfident on the test data also. In the training data, what you would see is that you completely exactly tell apart the ill people from the healthy people. So a reasonable way, well, not a reasonable way, but like some, what do we do in practice when we observe this overfitting behavior in deep neural networks? We do early stopping. Okay, we see what's going on before overfitting occurs. And here what we see is that actually during early stopping, the probability estimation is not so bad. Okay, so it's not as good as when you have infinite data, but it's actually really not so bad. Okay, and here, by the way, the predicted probability tend to be higher. So it's the opposite of what happens in the infinite data case. Okay, so
if I may ask, early stopping based on what criterion?
Cross entropy on a validation set. This is an excellent question, by the way, because I think that's pretty crucial, and I imagine that there could be better ways of doing the early stopping. Yeah, and as I will show you later on in our method, we actually rely on that, and I'm sure there's a lot of cleverer things to do. This is a very good question. Any more questions?
So I have a question. How do you, so that third plot, how do you interpret that dip again? So you can see like a deviation from the curve in terms of observed frequency.
So it looks like the predicted probabilities are higher than they should be. this is happening because we're not being able to, we're not able to learn, like we overfit to some extent, or it's difficult to tell, right? Because we're doing early stopping. So it could be some underfitting, some overfitting. Yeah.
So could it be not necessarily, well, I mean, if you're doing early stopping, I'm not sure I would call it overfitting necessarily. Maybe.
Yeah. So I didn't say necessarily overfitting. There could be some overfitting. So you could be overfitting part of your training set. There could be some underfitting. You haven't trained enough, and you haven't learned some features that would be useful to learn good probabilities. We don't know. Yeah, this is a good point.
It's weird that, okay, so those are for the ones for which the observed frequency is higher. So it's not like, maybe it's not like you don't have data of that type.
Say that again, sorry.
Sorry, it's just a bit counterintuitive. I kind of would expected the error to be on the other side of the plot for some reason, but maybe that's not.
I don't know. It's difficult to predict. So what we're doing here is we're binning according to our own model, right? And then we see what are the actual observed frequencies in the test set.
Yeah, that is true.
It's difficult. It is the test set, so that's important. On the training set, we understand much more what's going on.
Right.
The test set, not so much.
Okay. All right. Thanks for clarifying.
No problem. Okay, so this is actually a fundamental phenomenon. It is known that for finite data sets, models are going to memorize labels, even if they're completely random. So there was this influential paper a few years ago, which showed that you put random labels in a data set, the network will learn it. Okay, so this is not surprising. It's also known that during an early we call it early learning in my group, like maybe other people have other names for this, but during an early learning stage, the models actually do very useful stuff. And I just want to mention that we have actually exploited this to develop methods for classification from noisy labels. In the paper that we wrote about this, we actually show theoretically that this will occur even if your model is linear. So the problem is just that things are too high dimensional. Okay, the input is too high dimensional. You could even have a linear model that learns the zeros and ones. So this is a very, very general phenomenon that we have to deal with if we're going to have good probability estimation. Okay, I'm going to go a little bit faster now. In this work, we propose a model to improve probability estimation. And the idea is that during early learning, we obtain a model that is not too bad. Can we improve it without overfitting? And what we thought of was enforcing calibration. And by calibration, I mean the observed frequencies correspond to the actual frequencies while continuing to learn. We did this in the following way, but I think this is actually an interesting research direction. There are probably many other ways of doing this. What we did is we minimized cross-entropy loss until memorization begins. We know this because of because of cross-entropy on validation. And then we alternate between enforcing calibration. So we want to push the estimated probabilities so that they correspond more to the observed probabilities. For this, we have to bin based on the model output. So you need a model that is reasonable. That's why we need this first part. Otherwise, this will not work at all. And then we actually continue minimizing cross-entropy alternatively. Like one epoch, we do like we enforce calibration. One epoch, we enforce cross-entropy. This is what we found worked better. But again, we think that there's probably a lot to be done in this direction. Just to show you a picture, the blue line here is a smooth cross-entropy line. So when we train, what happens is, just let's look first at what happens here. There's overfitting. The training loss goes very, very low, and this corresponds with very high validation loss. And this is the probability estimates, because we have the two probability estimates and the synthetic data. Okay, so that's really bad. What we do is at some point, which is marked by this arrow, we say, okay, we're starting to overfit, let's stop and let's start alternating. And when we do that, we manage to train the model a bit better and in a relatively stable way. And we do get some gain in validation and in probability estimation. Okay, so that's our idea. And to show you what happens when we apply this on the synthetic data, we get, it's not super clear to see, but we do get some better probability estimates. Maybe it's clear in the bottom graph. Okay. You might be asking, okay, but like I'm sure there's other approaches to do this. Interestingly, when we looked at the literature, most other work that we could find, and we're happy to hear about any other work, focused obsessively on calibration in classification, because those are the benchmark data sets that the machine learning community has, which is a very important problem, but where there's no inherent uncertainty. However, it's a problem that is so related that you can actually just take those methods and apply them to probability estimation, and that's just what we did. Here, I'm just going to mention, like, we tried to basically pick what we thought would be the state of the art for calibration, and we wanted to apply to probability estimation. That included post-processing methods, where you just train a neural network, again, doing early stopping like before, and then you try to fix the probability estimates post hoc. Bayesian and ensembling methods, and some modified cost functions. Okay. Our conclusion after applying all of these methods is that a lot of them work pretty well. Our method works better, but like the differences in some cases are not dramatic. And it's possible also that part of it is because these methods were mostly tuned or designed for calibration for classification. And we do think that probability estimation has certain unique aspects that maybe should be taken into account when you're designing these methods. But the truth is that a lot of them work quite well. Our method, which is down here, actually worked very well. Again, as I mentioned before, Brier is probably the metric that you want to look at when you're evaluating probability estimation, but you could also look at a combination between AUC and ECE. So this is a calibration loss, and these are discriminative classification loss. Okay, so if you maintain good calibration, AUC is a reasonable way of comparing models side to side. Okay. I don't have a lot of time left, but I do want to show you the actual curves that we get for the real data. So in weather prediction, the green line shows you what happens if you do early stopping. The gray line shows you the next best method, which was deep ensembles in this case, and our method is in red. Okay, so we want to be close to this line, and we want to be as spread out as possible to be as discriminative as possible. That's kind of what we want. And it turns out that for this weather forecasting problem, the method works quite well. In collision prediction, we have a very difficult data set because there's very few collisions. There's a severe, if you want label imbalance, although here it's about the probabilities, right? So the generalization of label imbalance to probabilities, most of the time there's not that many collisions. You want to, you're going to have to train your models with a small number of actual collisions. It's actually an interesting research direction to see how to do better in this case. In this case, we do similar to the next best method, which is MMNC, which is based on a kernel measure. And we definitely at least improve early stopping, but this is a very difficult problem because of the fact that there's severe label imbalance. And finally, for our healthcare application, this is what we obtain compared to early stopping and deep ensemble. The deep ensemble is relatively well calibrated, but not very discriminative. We improve the calibration with respect to early stopping, and we remain quite discriminative. Remember that these are the predicted probabilities, and these are the empirical probabilities obtained from the test data. Okay, so quickly, conclusions. Deep networks can be very effective for probability estimation, but you have to be careful. Evaluation is very tricky, and it's very important to think carefully about what metrics you use when you're thinking about calibration. Exploiting early learning and enforcing calibration during training seems to be a promising way to improve probability estimates, at least from our experiments. And definitely more benchmark data sets are needed. So, we actually struggle to find other people that were even considering probability estimation problems. So we feel that there's a lot of potential for the community to focus on that, because some of these problems are very important, particularly in health. Yeah, and if you want more details, we have a preprint online. I don't want to, use Uri's time, but if there's a quick question, I can ask.
Thank you so much for your great talk. So please, if anyone has any questions, so feel free to ask.
Well, since it's my time, I'll just ask a question because I'm really curious about this. So, do you have any kind of theoretical insights about calibration in this over-parameterized regime? Like, how should we think about it?
So we have some theoretical analysis of a linear model, but what we can show is basically that in the end, you're of course going to be able to overfit the zeros and ones. And then at the beginning, you are going to be aligned. I mean, it also depends a lot on the generative model that you have for your probabilities, right? Like in this case with H, in our linear case, we also have like a vector that kind of, depending on where you are on this vector, that tells you which probability you have. So you can see that things average out at the beginning so that you're learning in the right direction and eventually you overfit. How much insight that linear model gives you to design, what to decide what to do with a deep learning model, I don't know. This is it's a very good question. I think the short answer is we have no idea, but we have some small insights, I guess.
Thank you.
All right, thank you so much for your talk. So our third speaker is Yuri Shalit, who will be talking about when and how can machine learning be used for treatment recommendation based on patient records. Dr. Yuri Shalit is an associate professor at Israel Institute of Technology. He received his PhD in machine learning and neural computation from the Hebrew University in 2015. Prior to joining the faculty, Yuri was a postdoctoral researcher in NYU and MIT. And one of Dr. Shalit's research area is applying machine learning to healthcare. So Yuri, we're excited to have you here. So please go ahead.
Thank you very much. Thanks for inviting me. Okay, so using patient data to personalize treatment is the notion that brought me into machine learning for healthcare. Like I was doing machine learning, other types of machine learning. I was like, no, I want to use machine learning to learn how to treat patients optimally. That seemed to me like the obvious thing to do. And it took me several years to appreciate that it's much more difficult than I had imagined coming into this. Now, this idea of using patient data to personalize treatment is really especially important when there are no clear clinical guidelines, which turns out is actually often the case. So the way we're imagining it is, you come see the doctor and let's say they diagnose you with some condition. They have, to simplify things, let's say they have only two treatment options, T0, T1, and sometimes they might not be sure what's best. And then the AI assistant, so Jenna talked about like AI and a clinician synergy working together. So maybe at some point they could ask, okay, what's the recommendation? And our model would say, oh, we recommend T equals 0, and hopefully that recommendation actually helps treat this patient better. Now it turns out that in order to do this, you have to think about causal inference, about causality. And I'll talk briefly about causality soon. But basically, if you're making any kind of algorithmic decisions in the world, you have to think about causality. Shortcuts become even worse when you're taking actions in the world. You have to be very, very careful. And this is especially true if your model, your machine learning model, is based on observational data, let's say data from hospitals or clinics or collected by patients, because this data generally could have confounding. Patients of a certain type might be treated differently, and your machine learning model might confuse correlation for causation, might confuse gender for treatment, age for treatment, or other more subtle confounders. And the most kind of difficult aspect, at least for people coming from machine learning, of this problem is we can't know if we're correct. So we built this, let's say we build a model which recommends for this patient should be treated this way, this one should be treated another way. We have no test set, we have no way to actually know beforehand whether our recommendations are true, because whenever our recommendations differ from what actually happened, we don't know what would have happened. We don't know the counterfactors. So that's kind of, that's where this really diverges from standard machine learning, where we have a test set and we can know how well we're doing. Here we can't really know, and this means we have to be much more careful even more so than standard machine learning for healthcare problems, which are in themselves, like of themselves, difficult. So what I'll talk today is how do we build confidence in such models and avoid harm, given all these difficulties, the difficulties of confounding, of no real test set. We still want to be to build the best systems we can going into deployment. Okay, so the scenario I have like in mind in this talk is, say you want to use patient clinical data to build a clinical treatment recommendation model, and we propose best practices framework for how to do this responsibly. So this will not be about like a specific algorithm, but about a framework about how to think about these kind of problems. Okay, so not focused on specific algorithm. And our framework has 3 phases. First is what's called identification. So it's figuring out, can the data even do what I want it to do for me? Second is estimation. This is even more familiar to kind of the most similar to classic machine learning. You estimate models and try to understand, okay, what does the data tell me? Does it tell me this patient should receive this treatment or the other, and so on? And finally, validation. So how much should I believe the model that I just estimated? And I'll talk about these 3 phases. But before I go into this, I just want to say identification, is sometimes called cause identification, is a part that might be less familiar to people coming from machine learning because it's not exactly data dependent. There's no statistical tests to kind of solve this problem. It requires understanding, going deep into the data, which is always needed in healthcare, but again, like maybe even more so. And there's several formal steps that you can do that help you know whether you can even embark on this quest to recommend treatments for patients based on EHR data, for example. Okay, so here's kind of the general, like how we imagine this problem. We have a patient coming in, we have her medical record, she has high blood sugar, and we're debating 2 treatments. We'll only talk about 2 treatments here just for simplicity, T equals 0, T equals 1. And we imagine this patient has 2 futures, like if she were to receive medication 0 or 1. And we denote these 2 futures in terms of her blood sugar as Y0 and Y1. And ideally, we just want to know these 2 futures for this patient. If we knew this is her future under T0, this is her future under T1, we'd know how to best treat her, which is to choose the future where her blood sugar is lower. Okay? And these Y0, Y1 are known as the potential outcomes described to Rubin and even going back to Neyman in the 20s. And the statistical quantity of interest here is something called the Kate conditional average treatment effect, which is the expectation of Y1 minus Y0 conditional on X, where X is the vector describing the patient. Okay, and ideally, we'd like to know Kate of X for every possible patient we might see. The problem with this is that we never directly observe this quantity that we're trying to estimate. We only ever see either Y0 or Y1 for any given patient. Anna, in our historic database, she got one of the medications. Maybe a year later, she switched medications, but a year has passed and she's after the first medication, so she's not actually the same patient. So really, this is known as a fundamental problem of causal inference. We only see kind of half of what we'd like to see. And moreover, which of the 2 futures we get to see for any patient is not random, because clinicians generally don't treat patients randomly. They have the reasons for choosing one treatment over the other. Maybe the reasons are misguided, but still they exist. So we get this biased partial view of the quantity we'd actually like to estimate. Okay. Any questions so far about this setup? One way to think about this quantity K of X is, what if we forced patients with features X to receive treatment T equals 1 versus what if we force them to receive treatment T equals 0? So forcing them in the sense of like cutting out the actual treatment assignment process. We want to know if they had to receive T equals 1, no matter what's the current policy or practice and so on. If they had to receive T equals 0, what would happen under these 2 in these 2 worlds, and then compare the 2. And X says is usually a high dimensional feature vector describing the patient. If we had known Kate, how would we use it? So it's pretty straightforward. The general idea is to estimate it for an incoming patient who would have Kate hat of X, and then present a recommendation to the doctor should they need it. Let's say if lower outcomes are better, so let's say Kate X is negative, we'd recommend t equals 1 because that means y1 is lower than y0. If k hat of x is positive, we'd recommend t equals 0. And maybe if we're not really certain, we want to defer recommendation. That's another aspect of being safe, saying, okay, sometimes we just don't know. And so we want this option as well. Now, there's been kind of an explosion of machine learning tools to estimate k. Forest, networks, Gaussian processes. There's a ton of it. I also did some work in the field. I won't go into these. What I want to talk about, though, is that all of these methods only work under a strict set of what are known as causal identification conditions. So I mentioned identification, which are that there are no hidden confounders, that there's common support between different treatments, and no interference between units. And I'll give some examples of these. But basically, it means that we've measured all the important factors affecting treatment and outcome, that patients could plausibly receive either of the treatments we're considering, that there's no kind of exclusions, and that the treatment of one patient doesn't affect the outcome of another patient. So if we're talking vaccines, for example, if I get vaccinated, it might affect the outcome of my family members, so that's a violation of interference. And the problem is that most of these assumptions, most importantly, the no hidden confounders assumption, they're not testable from data. So provably, there's no statistical test that will tell you this holds. So all these fancy algorithms work under some like really non-trivial assumption that there's no way to formally test. Okay, so that's kind of one of the major issues we have to deal with. So how do we build trust that this a condition of no hidden confounders holds, that we've measured all the important confounders, even though we can't test for it formally in a statistical manner? Any questions about this? So what is needed to move from the kind of the theory that says, okay, there's these conditions, these algorithms, to practice, to actually doing this with real world data and going into production eventually? And what we have in mind is this framework. It's kind of a guideline to doing this. And I won't go over all of this, but it's a series of steps you need to take. And some of these relate to identification, some to estimation, some to validation. And I'll mention a few which I think might be more interesting kind of in this context. So the first step in identification, making sure our data has the right features and can answer the question we're interested in, is just specifying the target system, which is kind of inspired by Miguel Hernan's target trial, which is just defining exactly what is the setting and context of the treatment recommendation system. That might sound trivial, but when you sit down and talk with clinicians, you realize that their process is really complicated. They talk, the patient goes, comes back, there's more tests, like there's not always like a single decision point. And really understanding where's the point that you want the algorithm to be available to the clinician is non-trivial and helps kind of clarify what do we want to do. So, and it has some failure points. So here are some points we propose for discussion with clinical partners. So is the treatment decision made by humans at a well-defined point in time? Is the set of possible actions small? If the set of possible actions is too big, we might just have kind of not enough data. Are there clear clinical guidelines? If there are clear clinical guidelines, we might not be able to help because the patients are always deterministically treated the same way. There's no way to estimate what would have happened had we been treated differently. Okay, so we only operate in cases where there are no clear clinical guidelines. Is there high variability in treatment decisions between doctors? There might be no official guidelines, but they're kind of de facto guidelines. Again, if there are de facto guidelines, we can't estimate counterfactuals because patients are treated very consistently. We can't estimate what would have happened had they been treated differently because we have no data to support this. Do they agree what outcome do they want to optimize for? That's also not always the case. So all these things might seem obvious, but I found that they really help. And often clinicians come with all these kind of ideas and problems, and we have this discussion and realize that your problem maybe is really important and fascinating, but unfortunately we can't help you. Once we define kind of the treatment and the outcome and so on, we want to understand, does the data we have, can it help us realize the system we're targeting? So have we measured all the known confounders? Do we have temporal separation? A very useful tool here is building a causal graph, which I imagine some of you have heard about. So we can, and this is an example of a partial part of a causal graph we built with our clinical partners to understand what confounders exist. So what factors affect the treatment here as drug and the outcome here, which is HbA1c. So what should be measured here? So this looks complicated, but there's kind of a rather simple way to figure out among all these features, which ones do you have to measure in order to have all the confounders, at least the known confounders. So this step is not algorithmic, really. It's talking with doctors and building this graph, and then maybe running a tiny algorithm to realize like what variables you need to measure. But this is really important. And what's crucial here is there might be kind of a failure mode here when we say, okay, we built this graph, we realize there are crucial confounders which are not measured. We can't answer this question. We need to go back to the drawing board to do something else, like define the question differently, measure more data, measure more features, something like that. And again, this might, I feel like this is sometimes unfamiliar to machine learning people, this notion that we might have a lot of data and measured a ton of stuff, but still like we haven't measured one crucial feature and that's it. We're like, we can't do this. Even if we've measured a ton of highly predictive features, if we're missing an important confounder, we might have a dead end. Okay. So that is some notion of identification. If we're satisfied that we've measured all confounders and we have a well-defined system and so on, then we could go on to estimation, estimating the Kate using many of those fancy models, estimating what's known as the propensity scores, which I won't go into. We could do that. But then we also want to validate them. So as I said, there's no traditional test set for Kate, but we ran all these models. We can evaluate kind of classic regression classification metrics, like squared error, AUC, just to see that our machine learning models are reasonable, that they make sense. So, and look at the features they're using, check with clinical experts. So this relates to Jenna's talk. If we see that our models here use really weird features, weird to the clinical eye, we might want to stop. Right. So I won't give all the examples, but if our models just have very poor performance, if their AUC is 0.51, maybe we don't want to do causal inference with models that are so bad. And like I said, they might use unreasonable features. Maybe we look at the implied recommendations by the Kate and they look really weird. Like the clinicians look at some of the recommendations and say, no way, that's true. Then again, we might have a point of, and we need to go back and re-estimate the models and see what's going on. Yeah, how much time do I have?
You have about like 10 minutes.
Okay. We want to be able to estimate not just the model, but their uncertainties. So what we called the deferral set. So when are we not sure enough about the Kate? So why would we not be sure? Estimation error, classically, finite samples, models are misspecified, distributions shift. We just have inherent noise like measurement error, outcome stochasticity. We might have causal error. We might have residual hidden confounding. Maybe we're happy that we've measured all known confounders, but maybe we've missed something. So it might not be huge, but it might still be there. And if we have too much doubt, we might wish to defer the decision. And now modeling all of these together is actually quite challenging, especially for high dimensional models. And we did, especially the causal error is difficult to reconcile with all the others. And we actually have some work on that in ICML NeurIPS from last year, where we looked in how to kind of model both the causal and statistical uncertainty. I won't go into the details, but basically we have this parameter which says, if we have kind of this much, like lambda, gamma equals something hidden confounding. I won't explain what's gamma. It's a bit too technical and I don't have enough time. But if we have this much hidden confounding, how much could our estimate kind of wobble around? And as you see here, the more this log gamma grows, the wider our causal intervals are. And we need kind of to discuss with the clinicians and have this kind of predefined level of how much hidden confounding do we think is reasonable, and get these intervals. And again, if the interval of the causal plus all the other uncertainty intervals crosses 0, like we're not sure if Kate is positive or negative, then we might wish to defer the decision. Let me skip this. And I want to spend a few minutes on some preliminary results where we actually ran this framework on real world data. And this was led by graduate students, Ron Gutman and Shimon Shaiba. So the first was with our partners at the Elite Research Institute, investigating the effects of 2 second-line anti-diabetes medications for type 2 diabetes patients. So these are patients who have not responded to first-line therapy, to metformin. So they receive second-line therapy. There are more than 2. I'll present results for 2 of the medications. And the goal here is to reduce blood sugar measured in A1C. And we had more than 50,000 patients and a lot of confounders, possible confounders. And oh, I'm missing a slide here. We built that graph that we've how much far back to have to go. So we built this graph with the CLELIT experts, which basically had to model what affects the outcome, what affects the treatment choice. For example, the HbA1c baseline sugar level might affect the way a clinician chooses to give one drug versus the other. Their glucose level might affect this. So we had all kinds of things, including trying to characterize what affects this in practice, right? They might be like, ideally, this should not matter, but in practice, clinicians also look at this. So we have to actually acknowledge that. So we built this and figured that we're happy enough that we've measured most of the important stuff, or that we have reasonable proxies for them. And we ran our pipeline, and I'll just give like a few kind of tidbits of our results. So this is the histogram of our Kate estimates in terms of delta A1C. So as you see, it's a bit shifted to the left. So most patients should have received one medication versus the other. Most of these changes are not clinically significant. There's only a small minority of patients for which really one medication makes kind of a difference, and they really should have received one medication versus the other, at least according to our model. So we had that. Where did we disagree with what actually happened? So we think that about 8,500 wrongly received sulfa, which is the older medication. About 1,000 wrongly received DPP-4. These are in quotation marks because we only trust our models so far. But what we found is most of the wrong sulfa were treated by general practitioners as opposed to specialists. And sulfa isn't so, and that kind of gives us a bit more confidence because specialists usually would know better which medication should be given. So our model kind of tends to agree with the specialists more than the general practitioners. If we look at patients who actually receive sulfa, so we think that about half of them should have received DPP-4. For about half, we have no recommendation. So we have a high degree of uncertainty here. The DPP-4, again, we think that the majority should have received what they've received. So we agree here with practice. Only a tiny minority, our model thinks, should have switched. And basically, when we kind of sum it up, we find out that personalization, it's not always worth it. Okay, so when we compared the difference between, let's say, just move everyone to DPP-4, the newer medication, versus personalizing, this person should get DPP-4, this person should get sulfa, they both have roughly the same overall outcome. So this is bad news for us, good news for physicians, because it's much easier to just say, just give DPP-4. They don't need to deploy some fancy algorithm. The true picture is more complicated because they're newer medications introduced recently, and we still don't have enough follow-up about them to actually have a decent model. So we're still not sure what is actually the optimal treatment given these newer medications, which are now in the market. I'll give another use case shortly, and that will be it. So here, this is in acute care. We have heart failure patients. Sorry, this is with Dr. Oren Kosky and Professor Doron Aronson from the Rambam Healthcare Campus, which is the Technion University Hospital. And we're looking at the following. We have acute heart failure patients. These are really sick patients. About a third of them die within a year of their hospital stay. a lot of them also within the hospitalization develop kidney injury. And this is related sometimes to the treatment they receive for heart failure. So the clinicians need to balance how they treat heart failure because their treatment might hurt the kidney function. And they tell us that they have really poor guidance about how to do this. It's not only that there are no guidelines, they really have no idea how to balance these things. And specifically, we're looking at diuretics. So we had about 2,000 patients who had kind of kidney injury and heart failure in the hospital. Again, we measured many covariates, and after a lot of back and forth and saying, oh, we also need this feature and also need this feature until we're satisfied that we kind of have all the important confounders, we went through and estimated our models. And empirically, just kind of to set the stage, about half of patients had increased diuretics and half had empirically decreased diuretics. And we saying, okay, maybe we should decrease instead of increase or vice versa for this patient. And decreased diuretics, this treatment is the one that improves kidney function, but might hurt cardiac function. And really, we need to balance these multiple outcomes, but we're here only focusing on kidney function because measuring heart function turns out to be more difficult to get the right data for that. So we're not yet to that. So increased or decreased diuretics. The way we measure our model, so we don't have a true test set. We don't know for real what would have happened. We might have hidden confounding, but we have proxies. Our proxy is what's called the policy value. And it means the following. If the patients were treated according to our recommendations, how well would they have done? And this is measured in percent return to baseline here. So 100% means their kidneys are cured back to baseline. It's great. 0% means their kidneys are in trouble. So higher is better. And this is the same policy value as policy value in reinforcement learning. It's the same concept. Only here we have just one action, which is like increase diuretics or decrease diuretics, and that's it. Our models had recommendations for 460 of the patients. So we deferred for 69 patients and made a decision for 461 in the test set. We used doubly robust estimators, bootstrap confidence intervals. I'm happy to talk about that offline. And this is what we found. The policy value for increasing diuretics to everyone, just giving everyone one of the treatments, is about 20-something%, which is not great. This is what actually happens in practice, what's called here doctor's policy. So this is the way patients are treated now, and the policy value for that is about 25%, which is slightly better, so not statistically significantly better than increasing care. This is random policy. This is just finding treatment randomly, and it's about as good as doctor's policy. And we honestly thought we had a bug when we saw this, that random is as good as the doctors, but the doctors reassured us that they truly believe they might not be better than random the way they're doing this now. This is decreasing for everyone, which actually is better in terms of kidney function. And this is the machine learning policy. So the machine learning policy is better than current practice, p-value 0.015. It's approximately the same as just saying decrease for everyone. However, here, unlike the previous case, personalization matters because decreasing for everyone might hurt cardiac function. But our recommendations only decrease diuretics for 50% of the patients, so we give the doctors more flexibility with respect to the other outcomes they're trying to balance. We are trying to get the other outcomes kind of to figure them out, and that's still a work in progress. Okay, so should we believe this? As I said many times, we don't really know what would have happened if our recommendations would have been followed in cases where they differ from what actually happened. The only way to truly know if our recommendations are useful is to run an experiment testing the system with real physicians, real patients, and actually affecting treatment, which is scary as a machine learning person, which is why I gave this entire talk about how to build confidence in this model before we actually do this, before we can run an experiment, okay? So we want to come in the best possible safe shape towards such a trial. That's it. I want to thank Rome and Shimon, the students who led this work, and our partners at Rambam and Elite Research Institute who helped us immensely with the data, with the graphs, with clinical insight, and so much more. And thank you very much for your time, and I'm happy to take any questions.
All right, I think there is, thank you so much for your awesome talk. And I think there's one question from Professor Wins, Jenna Wins, in the chat.
Yeah, I'm happy to just ask it. I really liked this roadmap that you laid out in terms of taking some of this work in causal inference to clinical practice and talking to clinicians. And one of the things that we found when talking to clinicians about selecting treatments is oftentimes they're more interested in a ranking of individuals. So given 100 patients, who's most likely to benefit from the treatment. So what are your thoughts on optimizing for a ranking over something like root mean squared error or p-he?
I'm looking, no, I don't
You
have
have
the
a slide
ranking
on it.
Well, not in this version of the PowerPoint, so I won't start yeah, rummaging through my presentations. Yeah, I totally agree. So, but there are two different things. So there's the best way to estimate Kate, just saying what's the best treatment, or what's not even just the treatment, like what would happen under the two alternatives or multiple alternatives for this patient. And this could be optimized with whatever you want to get the best result. And then you can separate this from ranking. Then you can rank and say, these are the patients that will most benefit because they have the highest Kate. I will say there's a paper just out saying causal decision-making is not the same as causal effect estimation. So, which says you should not separate these two. You should not first estimate the effect for each person and then make a decision. You should estimate the best decision directly. And that's kind of like the difference between classification and regression. So I haven't yet thought about how that framework connects with what you're saying about ranking, but that's an interesting direction. It's saying not only causal decision-making, but causal decision-making in terms of ranking should also be, like following this new paper, should also be different, or could be made more efficiently than doing it separately, which is what we and most people currently do. So short answer is we do rank, but we do it separately from the effect estimation. It's an interesting direction for future research, saying how could you estimate directly more efficiently for the purpose of ranking.
Cool. Thanks for the pointer to that paper.
All right. Thank you so much. So our next speaker is Professor James Zhou, who will be talking about lessons from evaluating and debugging healthcare AI in development. Dr. Zhou is an assistant professor of biomedical data science and computer science and electrical engineering at Stanford University. He works on making machine learning more reliable, human compatible, and researches on in applications in human diseases and health. He received his PhD from Harvard in 2014 and was at one time a member of Microsoft Research. And he received a lot of supports from NSF Career Award and the Google and Tencent AI Awards. So James, we're excited that you're here, and please take it away.
Great, thank you very much. Thanks to the organizers. And it's really nice to meet all of you. Look forward to this discussion. It's also been really nice to learn about the exciting works from the earlier speakers. So let me bring up the slides. Great. Yeah, so what I want to discuss with you all and maybe get some of your feedback on is some of the lessons that we learned from actually trying to deploy AI in practice. Right. So a lot of the work that I've been doing in my group over the last few years have been more on the sort of foundation or model building side of machine learning. Right. So these are the kinds of things that's that we publish in NeurIPS ICML. We build a model and test it on different data sets. And recently, we've also been very interested in taking these models that we have and actually try to deploy them in hospitals, both here at Stanford and also across other hospital systems. And there's some really interesting, I think, challenges and technical challenges we run into when we think about really deploying AI models for a variety of healthcare applications. And I just want to use this time to get some of your thoughts and to share some of the lessons that we've learned. And just to give you a couple of examples of the kind of things that, that we are working on and we have been deploying. So this is, for example, one paper that we wrote in Nature 2 years ago, where we developed a computer vision system to look at cardiac ultrasound, because these are kind of ultrasound videos like here on the left, and to basically automatically diagnose heart conditions. Right. So the paper was published in 2020, but there's actually a lot more work and there's actually a lot more challenges from deploying this model, so which is now being deployed at the emergency department here at Stanford and also at another hospital, Cedars-Sinai. Another example of the things that we're trying to, in the process of deploying right now, is a tool that we built for clinical trials. It's called Trial Pathfinder. So we published this paper last year in Nature. The work is led by Rishan. And now we're in the process of deploying this at Roche Genentech, which is I think the largest biopharma company, where it's being used to inform the designs of some of their cancer clinical trials. Right, so quite a different space, because this is more facing, not patient facing, but more facing towards clinicians. But also there are a lot of really interesting challenges that we run into here. Okay, so when we think about challenges for deployment compared to challenges from building models, right? I think there requires sort of a shift in mentality and perspective, right? From think about building algorithms more about how to evaluate and monitor algorithms. Because that's sort of the first big challenge that we ran into. And just to make this very concrete for folks here, as I was going through one recent case study that we did. So we were trying to work with the Stanford Hospital, the dermatology department, to deploy AI models for dermatology, right? Which, as you know, has been part of a very active area of research for the last few years. Right? So companies, like Google and other commercial entities are also releasing dermatology systems. And basically how they will work is that patients can take their phone and take an image of their skin lesion, and these algorithms will basically run some computer vision in the background and give a real-time feedback on, in this case, that this is predicted to be melanoma, and provide recommendation that the patient should visit dermatologists as soon as possible. Right. So if this works, then it's great, because there are millions of people who actually have skin cancer every year, but they're not diagnosed until it's too late. So we took 3 of these original, these sort of either commercial or state-of-the-art dermatology AI models. They all had very high reported accuracy, AUCO about 0.9 in their publications. So we tested them on Stanford patients. So these are real Stanford patients, right? And the performance was just substantially worse, as the AUC dropped from 0.9 to 0.6. And just to be clear, these are just real patients. There's no adversarial perturbation or cherry picking of the patients. We just took their images, right, from the Stanford EHR. So the first challenge that we were into this stuff is, how do you actually explain what happened here, right? So we did a quite systematic audit of these dermatology AI models, and I'll just first show you the results of the audit, and then I'll come back in a few slides to explain a bit more about what are the tools that we developed to do these kinds of audits systematically. So in this particular case, right, so the audit is basically trying to explain the drop-off phenomenon of essentially, like, why is there this large gap, right, from the original publications of 0.9 to larger than 0.9 to when we tested on Stanford patients about 0.6. So one factor that we identified, right, is that actually there were just a lot of mistakes in the labels of the original data that we used to evaluate these models. Right. Maybe it's not something that was obvious to me from a machine learning developer, but this is actually explains about half of the mistakes. So what ended up happening was that these original dermatology models, right? So the test sets for these models came from having a set of dermatologists visually looking at images and say, is this benign or is this malignant, right? And that's easy to collect because you can just visually look at these images. And it turned out that visual inspection even by experienced dermatologists can be very error prone. So the actual ground truth in practice in clinics come from taking a biopsy of these lesions and doing pathological testing, right? So which is the ground truth that we have here at Stanford, right? So actually, because there are so many mistakes in the original test sets, that actually explains the large part of the drop off in performance. The second big factor that we identified is there's quite a large data shift, right? So the original data was trained on mostly common skin cancer diseases because it's, again, easy to collect. Here we have both common patients, right, and also less common diseases, right? So that actually also explains a substantial part of the drop-off. And third factor, which is also very critical, right, is that we identified that all of these models were just substantially worse on darker skins, right? So the sensitivity of the model, which is, if you have skin cancer, how likely is the model able to detect that you have skin cancer, right, is very low on images from darker skin patients, right, compared to other patients, right? And the one reason for this is that there were just very few images from darker skin patients in the original training or the test data sets. So this is one example, right? We try to do these systematic audits basically for a lot of other medical AI systems that are being deployed, right? So we actually did an analysis of all of the medical AI systems that were recently approved by the FDA. So as of 2021, there are about 130 of the FDA-approved medical AI systems, right? So here's just a summary that we made of them, right? And more details are in this paper here. So basically, each of the symbol here corresponds to one of these 130 FDA-approved AI systems, right? So these are actually approved by the FDA and being used on patients. There's a bunch of information here, but I just want to highlight one thing, which is I color-coded each of these algorithms. So they're stratified by which body part they apply to. And I color-coded these algorithms based on which ones actually reported evaluation data from multiple locations, right? Those are coded in blue, and which ones did not, which are coded in gray. Right, so one thing that's actually very striking is that most of these algorithms, 93 of 130, when they were applying for the FDA approval, they did not actually report multiple site evaluations, right? The other thing that we thought was actually quite interesting and also quite potentially interesting limitation is that only 4 out of these 130 devices were tested in prospective studies, right? So 126 out of them were tested on retrospective data, basically data that were previously collected before the algorithm was deployed, right? And the only retrospective data most of the time from this one location, right? So, as machine learning researchers, that's starting to ring a lot of red flags, right? So we saw from the dermatology case study that I mentioned a couple of slides ago, if you only have retrospective data from just one location, right, that can potentially mask a lot of limitations of the model, which are important to identify for deployment. Okay, and I'm also happy to take any questions if people have any. Just feel free to speak up in the middle. Okay, so from this experience of trying to audit all of these models and also deploying our own models, right? So here's a few of the lessons that we've taken away from doing this, right? From how do we really build and to deploy AI models that we think are trustworthy, right? So the first one is really about, we have to be much more transparent about what data is actually used to develop these models, right? And then the second point is that we need to put a lot more efforts into actually cleaning these data sets, right? Which also falls under this recent umbrella of data-centric AI. And to also, I think it's also critical to understand specifically why these models make mistakes in deployment, right? So we want to have basically very fine-grained explanations, understandings of model mistakes. And the last point is really, we found it to be super important to do much more human-in-the-loop prospective evaluations. So it's moving away from these retrospective testing. So I'll just say a little bit about each of these points to flesh them out a bit more. Data sets as used to train a lot of the medical and healthcare AI models are fairly opaque, right? So just to illustrate this, we did another survey of basically all of the data sets that are used to train dermatology AI models, right? Following up from our initial case study. So each square here corresponds to one of these AI in dermatology papers published papers. And the circles corresponds to the data set that was used to train that model, the model in that paper. And I color coded the circles, right? By, if it's red, that means that that data set is actually a private data set that nobody can access. And there's very little information about that data set. And the ones that are in green are the public data sets, and the size of the circle corresponds to indicates the size of the data set. So one thing that you note here is that there's a couple of large benchmark data sets that are public, right? This number one here, it's a data set called ITSIC, so it's public, and a lot of people use them for training and for evaluation, right? So that's useful. On the other hand, there's about half of these published AI models, right, that are essentially just using relatively small private data sets that nobody have access to, so they can't really audit them. And there's very little information about what is the composition of those data sets. Right, so we couldn't really find, for example, the distribution of skin tones in any of these data sets or in many of these data sets. So that's, I think it's a huge limitation for our community, for the field. Right? And some of the things that we try to do is to really, and there's a lot of great efforts recently of trying to release a lot more data sets, right? For example, I mentioned that we're developing this and deploying this cardiology model. So we actually released all of the data that we used to develop that model. So I think it's currently maybe the largest publicly data sets of medical videos. Right? And we also released all of the annotations of patient information. Right? It's a lot of work because you have to make sure it's safe and de-identify them. But there is a pathway to actually release all of this data, right, to make it very easy to access for people to use. So second lesson that we learned is that I think it's actually really critical to think about this data accountability, right? And which is closely related to being able to clean data sets in AI, right? And by accountability, I mean something very concrete mathematically, right? Which is, let's say if the model, you have some particular training data sets that you train your favorite model, right? And achieves whatever performance, we would like to be able to essentially attribute the performance of the model to the individual data points or to the individual sources of the data, right? And in particular, if the model makes mistakes, right, I would also like to have fine-grained attribution of which exact training data is responsible or contributes to those mistakes, whenever that's possible, right? So if we can have that level of attribution from the model's deployment to the individual training data, then we can make the whole system much more accountable in practice. Right, so we did this again with this the dermatology example. So this is uses a set of techniques that we call the data Shapley values. And what we do here is that we take these models that are trained, right, and we deploy them and test them on clinical data, right, from patients. And we can see, as we saw, we see various drop-offs in the model's performance, right? And part of that, as we saw, is because there are all sorts of noise and misannotations in the original training data. Right. So basically what this data Shapley score does is that it essentially computes a score for each training image. Right? It could be a score could be positive or negative. Right? So the ones that are negative, so the score basically is a way to estimate how much did that specific training image contribute to the model's performance in practice. Right? So if the scores are negative, that means that those images are either misannotated or contributing various noise or outliers or biases in the model. Right. And one simple way that we use to sort of clean the data set is to basically to essentially filter by the Shapley values. Right. So once we filter out the ones with negative Shapley values, the remaining data sets, then we just retrain the model on the remaining data points, right, and deploy those, and those ends up just working substantially better on the clinical images or in application. So I guess the benefit of this approach is that we didn't have to, oftentimes it's hard to actually collect additional new data, right? But it is reasonable in practice to clean the existing data, right? And that's something that we're able to do pretty efficiently with data Shapley values and also a lot of other great works recently in this area of data cleaning. So the third factor we thought was actually quite useful for us, right, is to basically to do these kind of audits where we really try to explain why did the model make these specific mistakes, similar to the example I mentioned in dermatology. Right? So here, we basically want to have some sort of natural language explanations, right, of why the model made certain mistakes, natural language, because then that's easier for us and also for our clinical partners to understand. So we developed this approach, right, based on essentially making counterfactual perturbations to each image, right, to try to come up with explanations for why the model made specific mistakes. So here are just some examples of applications of applying this approach, right? So these are 4 example dermatology images where these commonly used models all made incorrect predictions. So the correct label is on top and the incorrect was at the bottom. And in each case, this approach that we have is called counterfactual explanations of mistakes. And so the output of this is basically an explanation of why did the model actually make a mistake in each of these instances. Right? So for example, for the first image, so we were able to detect that the reason that why I actually made this mistake specifically because of the skin color, because of the dark skin color. Right? And it's able to arrive at that conclusion because it makes a counterfactual perturbation to the image that says that okay, if you change the skin color, the model would have gotten the correct prediction. In the second instance, right, so we identify that, oh, the model failed here because it's actually too blurry, right? So that's the actual explanation of the mistake. The third one is too zoomed out. And here in the fourth one, the mistake is because there's too much hair, right? So basically by making these kind of counterfactuals and then providing sort of a high level natural language explanation of why the model makes a mistake in each of these instances, that makes it a lot easier for us to evaluate and to debug these models. Yeah, and the last point I want to mention, it's the importance of really doing more prospective human loop studies. So if you think about medical AI, like most of the time, we're actually optimizing the wrong objective, right? So we're often just evaluating how well the model works on a fixed data set, oftentimes a retrospective data set. But what we really care about is how well does the model work in deployment. And in deployment, oftentimes the model is not acting by itself, but it's oftentimes acting like maybe a second reader or a device to a human decision maker. Right? So what we really care about is how well does the model work in improving the human decision maker's final performance, right? Improving that team's performance. So we developed the various tools for just making it very easy to do these kind of prospective studies. It's called Gradio. Right? So what Gradio does is that it's in basically one line of Python, it creates these interactive user interfaces for any machine learning model. And then we can it also creates these links so that our collaborators, the users of the model can just open up these models on their web browser and they can just provide us real-time feedback for the models. Right? So Gradio is now used by I think, over tens of thousands of machine learning researchers and people from all these different companies. And we actually use this to test our models for deployment. I just wanted to finish by showing you one interesting example of something that's quite surprising to us that we learned by doing these really human loop perspective studies. Right. So the way that we design the studies should basically sort of mimic the actual clinical workflow, right? So in this case, right, so the dermatologist would say, okay, like, would you take this image? Would you want to biopsy it? Right. Maybe they would say, no, we would not want to biopsy, or they would say, okay, we want to biopsy. Right. So that's actually follows very closely with their clinical workflow. So where the AI comes in is that the AI is not going to make this decision by itself. Right. So oftentimes the clinician would take a look at this image. There's some initial judgment, right? The dermatologist have a prior, and then the AI also makes a decision that says that in this case, the AI suggests that, oh, maybe it's good to biopsy this, right? So we provide like a slider interface so that the AI would also indicate the confidence in how much it thinks that we should biopsy this. And then what we do in our experiment is that we track how much the dermatologist or the user changes their advice based on the AI's feedback. Right. So the dermatologist makes some initial recommendation, right? Maybe they're unsure in the beginning, then they see the AI feedback, and the dermatologist may decide to change their mind, and this is their final output. So basically what we actually evaluate is how good is the dermatologist's final decision compared to their initial decision conditioned on the AI feedback that we give in the middle. Right? So that's the real performance metric of the AI. And here's sort of the interesting and maybe it's surprising result for us. Right? So we tried several AI models. First, all these models, they all give exact same predictions, right? So they all have the same accuracy, but one model is calibrated, right? So it gives calibrated confidence, and the other model is not calibrated, right? So it actually gives overconfident predictions, right? So in machine learning, we're sort of taught to think that calibrated models are actually good, right? I mean, calibration is something good in practice. But in this experiment, when we evaluate how well does the final human perform, we found consistently that the models that are not calibrated systematically do better than the calibrated models. Right? Again, the models all have the same accuracy. The only difference is whether they're calibrated or not. Okay. And there's actually quite an interesting, maybe intuitive reason for this, right? Is that like the human user, they're also not calibrated themselves. Right. So if the model's performance or if the model's confidence is less than some threshold, if it's like less than 0.8, and humans are simply just going to ignore the model's evidence, and they're not going to change their mind. Right? So they're not going to change their second final decision compared to the first one if they see the model is not sure. So humans also basically have this activation bias, right? Which means that in order for the model to actually really help the human, the model would actually have to pretend to be more confident in these recommendations than the model is, right? Because otherwise the human is simply going to ignore that feedback, right? Which is why in this case, right, having actually uncalibrated models ends up helping the end users much more than having calibrated models, right? And these are the kinds of things that we would not have discovered unless we actually do these human loop prospective studies. Okay, so here again, I think just summarize the main takeaways, right? So I think as a community, we need to be much more systematic, careful, and transparent about the data sets that we use and to release those data sets. I think data cleaning is often really important in biomedical AI. And it's also really important to understand, to give these high-level explanations of why models make specific mistakes. And all of this tying together was using these sort of human-in-the-loop perspective evaluations. Right, so here again, the references for the various things I mentioned, we didn't have time to go into too much of the technical details, but all the details in the papers and the data are all available on our website. Yeah, so I'll stop here and happy to take any questions.
Thank you so much for your great talk. So is there, if any question, so please ask James. If not, so there is a break from like 10:45 to 11:30, and the next talk would be at 11:30. I will also put the so the first poster session would be from 10:45 to 11:30. So I'll just put the link in the chat for the ones who want.
A question?
Yes, please.
Thank you for the presentation. I have one question about human in the loop. So I was wondering how we could determine the number of participants for the efficient human in the loop process.
Oh yeah, so it's a good question. So in our experiments, I think typically in order to get like statistically significant results, we had on the orders of hundreds, let's say like 200 to 500 human participants. In some of these experiments that require more clinical expertise, right? So it's often hard to recruit 500 doctors to do the experiment. So there, what we can do is we have on the orders maybe like 30 to 50 doctors, but we try to get more feedback from each person. So basically from each doctor, we try to get on the orders like 30 to 50 small tasks we ask them to do. So that helps us to get enough sample sizes.
Thank you.
Can I ask a question?
Yes, please.
Okay, thanks for a great talk. I'm a PhD student in Illinois Institute of Technology. I'm very interested in expandable AI. And may I ask, how do you think about the reliability of sharp-learned value, maybe as explanation, and how can we improve the reliability and how to evaluate the reliability of explanations such as the sharp-learned values?
Yeah, it's a good question. So we have a lot more experience with the data Shapley values than with the feature Shapley values. So I'll say a bit more about data Shapley values. And so I think the way that we evaluate the data Shapley values is, in our initial papers, basically we say, okay, so if the data Shapley value of these points is negative, then after removing those points, right, if we clean the data set by removing those negative points, now how much does that actually change the model's performance, improve the model's performance on some new data sets, right? Maybe on my clean evaluation or test deployment data set. Right, so that for us is like a pretty natural way, because if the goal there is data cleaning, right, then we just want to say, okay, if I remove these points with low and negative Shapley values, how much does that improve my model's final performance?
Yeah, maybe there are some like spurious correlation, maybe impact.
Yeah, so I think this maybe it's true. So spurious correlations, I think, are more like the factor for the feature Shapley scores, right? Because there you have correlations among the features. I think that's less likely to be a correlation for the data Shapleys, right? Because it's true that certain data points can also be similar, but the Shapley value itself, the way it's computed, actually accounts for that similarities between data points.
Okay, thank you very much.
Hi, James. Just a quick question in line with that. Yeah, great presentation. Thank you. So usually the Shapley values are sort of ranking the data points, and I saw the latest beta Shapley value as well. And I was wondering, apart from individual data point ranking, how could we extend that into sort of group of data points which probably came from similar data procedure or a single site, or they are characterized by similar feature characteristics. Any hint on how we could extend that into sort of detecting subgroups of data points that are less relevant or highly relevant for the prediction?
Yeah, I think that's a great question, and it's also like a great direction. So one thing that we could do is so it turns out that we could also apply data Shapley value to sets of data points, right? So where each unit of analysis is a group of data rather than being one data point. So I can treat that one set as basically one unit to compute the Shapley value. And then the output of the data Shapley value then would be, for each set, what is the value or the contribution of that set? Right? So that's one way that we could extend the data Shapley value to compute values over groups of data points. And we have actually used this approach to evaluate data from different hospitals. So there, we had data from 20 or few different hospitals, and we treat each hospital as basically one unit. So all the data points from that hospital is one unit, and the Shapley value would give like a number for each hospital that says that, okay, this hospital actually contributed a lot of noise, and these other hospitals contributed high quality data.
But in that, already from which hospital those data points came from.
That's right. Yeah, if we didn't know which hospital data point come from, then I think that's an interesting challenge that we don't know how to solve. It's then we still need to have some ways to come up with the groupings, maybe by some other metadata. Maybe like the types of instruments, right? Maybe there's some other natural metadata that we can use to group the data points.
Cool, thanks.
All right, thank you so much. So if there is no questions, so you guys can go ahead and go to the link that they sent in this chat for the poster, the first poster session. And we're gonna come back at 11:30 for Professor Fei Wang's talk. And thank you so much.
Thanks, everyone.
Thank you. All right, everyone. So welcome back. And so our next speaker is Professor Fei Wang, who will be presenting machine learning for analyzing patient health data with small n, large p, and the implications. Dr. Fei Wang is an assistant professor of healthcare policy and research and received the Faculty Early Career Development Award from the National Science Foundation for his work developing computer models used to predict diseases. So Fei, we're excited that you're here, and please take it away.
Thank you, thank you. First, I want to make sure, can you hear me okay, and can you see my screen?
Yes. Okay,
great. So thank you. Thanks for the introduction, and thanks for the invitation. And again, I'm currently an associate professor in the medical school of Cornell, and I want to talk about machine learning for analyzing patient health data, particularly small n, large p. Here n is the sample size, p is the feature dimensionality and the implications, and it's essentially a summarization of a lot of the works that has happened in the past several years in my lab. So first, I think with this audience, I don't need to explain too much about what is AI and the potential of AI that can be helpful of solving healthcare problems. And of course, we're in a stage where we have a lot of data around the patients, and we are emphasizing a lot on the notion of precision medicine, ensure that it's providing the right treatment to the right patient at the right time in order to understand these rights. So you have to really integrate information from all different aspects, like Francis Collins pointed out when he put forward this precision medicine initiative. You really want to integrate the data from all different scales and different places, and this needs novel computational approaches. Here, a novel mostly comparing to conventional statistical, mostly hypothesis-driven approaches. And there are, of course, a lot of exciting advancement of application of AI in medicine in recent years. These are just some examples of the papers published on major journals. And but at the same time, there are also a lot of challenges that makes healthcare or analyzing patient health data different than the conventional data we already analyze in computer science. So let me give you two examples. The first example is this paper. I bet most of you have read this paper. This is the first paper from Google. On analyzing electronic health records, published on MPJ Digital Medicine. And so essentially, they kind of like leverage the electronic health record repository from two major hospital systems. I think one from California and one from Chicago, and they try to leverage the data to build a machine learning model for three pretty important and popular prediction tasks. One is inpatient mortality, one is 30-day hospital readmission, the third one is a hospital length of stay. And they kind of like compare the sophisticated deep learning model, which is shown here. There's actually an ensemble of three models. One is weighted recurrent neural network. The other is feed-forward neural network with time-aware attention. The third one is boosted decision stop. So their final model is actually an ensemble of these three models. Of course, different, each of these three components are added there for particular purpose. And as a comparison, their baseline model they compare to our simple linear model, logistic regression probably plus some regularizations. And if you look at their performance, as I said, there are two major hospital systems. If you look at, across the three tasks, if you look at the first row in each of the section, this performance achieved by their complicated model. And the following three rows are different version of the linear model with different features and as you can see, if you look at really the performance plus the confidence interval, you don't see too much difference. I mean, if you consider the model complexity, right? So this is, I mean, a little bit counterintuitive compared to what we usually see. I mean, in computer vision and let's say speech recognition, natural language processing, if you use, these advanced deep learning model, you can see a big bump. But here, at least for this paper, we didn't see that. And this is another paper, done in my lab about 4 years ago. And we actually leveraged a machine learning model to, help with the task of hospital readmission prediction for COPD patients. COPD stands for chronic obstructive pulmonary disease. And actually, initially, this is a collaboration with American Air Liquide, and we use the Geisinger data. It's pretty good data, and initially we do this is we try to show because this 30-day readmission prediction is a difficult task. So we thought, conventional like linear logistic regression or whatever tree type of model cannot do well. So we think perhaps deep learning model can beat them easily. So that's original intention when we do this task. And of course, we did a thorough literature search to understand the landscape, like this hospital score list, LACE index are the popular clinically used criteria for hospital readmission risk assessment. And we call these knowledge-driven features and data-driven features. And data-driven feature, of course, is a DX diagnosis and procedures and pharmaceutical features, which are essentially medications and locations. And hospital score LACE are the features they use in those clinical use criteria. And we did some enrichment based on handpicked the features. So and if you actually, I don't want to explain all the details, but the long story short is we have tested all different kinds of deep learning model architectures, including feed-forward neural network, recurrent neural network, convolutional neural network with, of course, longitudinal EHR matrix representation. And we have tested different kinds of representations, different types of embeddings with different time intervals. But doesn't matter how you change this. If you compare with the conventional model, logistic regression, it's a little bit weak, but in this case, random forest and gradient boosting tree performs pretty well. And it is just very difficult for those advanced, deep learning model to beat these conventional statistical model. So this makes us thinking of why it is like this. So what makes these healthcare data, especially electronic health records, different than those conventional scenarios? Not really conventional, but more prevalent scenarios like computer vision, like natural language processing type of stuff we see in computer science tasks. So if we think about for computer vision tasks, let's say image recognition, right? So convolutional neural nets can really do a fantastic job. It can easily beat those conventional image processing type of technique. There are, of course, a lot of reasons, like those images, they have some intrinsic structures and a lot of characteristics that, convolutional neural nets is built upon. And another important characteristic is, doesn't matter how difficult it is to the computer, it is very intuitive and straightforward to human. So, recognizing something in an image is never a difficult task for human. And of course, it is fairly easy for you to get a lot of image data almost for free. And same thing for speech recognition. That's another task that deep learning models have been demonstrated to be super powerful. So you still have all those, patterns or fixed characteristics of speech signals, and it is never difficulty for human to recognize what another person is speaking about, and also same thing for natural language processing. So, some common characteristics for these data that machine learning models have demonstrated to be super powerful. Number one, so they have some intrinsic structures of those data. Number two, it is not a difficult task for at least a human to understand the problem, solve the problem. And number three, it is relatively easy for people to collect more data if the data is not enough on those domains. But healthcare doesn't satisfy any of these criteria. And even for those popular scenarios, let's say computer vision, we still see these car crashes and autonomous driving system in the cases where the thing has never existed in the training data. This is also for GPT-3, a monster natural language processing based model. So if you, of course, intentionally, manipulate your question and ask the GPT-3 to help you complete the paragraph, it can, come up with some absurd, completions. So this is really because, like, the computer or the model is trained in a way that it learns what is seen for the connection patterns of the words. And in the previous case, what it trained on, what it has seen, the common, natural things, the model was trained on. And in case of deliberate, manipulation on the data, or some rare cases where it is, not trained on, not in a data set. These sophisticated models still have difficulty, even in those areas or scenarios. It has demonstrated to be capable of doing very well. So then I think, if you think about healthcare, for most of the diseases, we don't understand what is happening for those diseases. So that means that the problem is super complicated. Number two, it is never easy for anyone to get more data. A lot of times I'm talking about patient health data. You just have 7 billion people all over the world. If you think about, of course, there are also privacy concerns. If you think about the patient population, who have data and you have access to, is typically restricted to one or just several hospitals. And if you focus on studying a specific disease, the population size is even smaller. So that means that we have a much larger problem space, or much more complicated problem space. And we have, a much smaller sample size. And it is never easy, or most of the time it is impossible for you to get more data. So in this case, how can you perform effective machine learning? That's why it is really small n scenario. Large P means that because we have the small n, so now more and more with the advancement of more and more technologies, imaging, electronic health records, wearable devices, whatever, you can capture more and more information, health-related information around every patient. So you definitely have your feature space larger and larger. So that's what I mean by large P. So really, we are in the scenario, almost for all the healthcare problems, we are in a scenario of small and large P scenario. But a lot of the times, by default, we assume that the scenarios machine learning algorithms are good at are in the large N scenario. So how can we do effective machine learning in this type of context? So I wrote several viewpoints, or review articles trying to claim some of them ideas I think that are important to this field. Of course, one is data, one is model. Around that, one is how can you solve the data, the sample limitations. What if you don't have, that's a small n part, and this is, of course, when your sample size is small, you train a model on one data set, may not necessarily work on another data set. So this leads to some bias problem. And of course, I mean, because your sample size is small, so it is hard to justify the generalizability. So then one way to convince the doctors or whatever, the decision makers, use that is to enhance the model interpretability. So interpretability is important. And the last is we talk about the data privacy is important, but now you have these more and more complicated models, and the model can encode a lot of information. So the model security is also important. So these are just some important aspect that I want to talk about and go through some of the example studies that my lab has done in the past several years. So first is regarding the sample limitation. I mean, the small and large p side. So because the sample size is small, we want to gather more and more information for every patient to better understand the condition or the status of the patient, so that can lead to better decision making. So multi-model or multi-view type of learning is important. That's the way how you consider how can you do integrative learning for heterogeneous features, heterogeneous information. So this is a paper we have done like several years ago about in electronic health records. There are two parts. So one is structured fields, like those codes, diagnosis code, procedure code, medication code, and the other part is unstructured information, which are the clinical notes. And these two parts of information, they contain complementary information about the patient. So how can you combine them? So we build memory network type of stuff where we use hierarchical LSTM to process the nodes, and we use a memory network to process the structured fields, and then we combine them all together to make a prediction. I mean, in this case, would be the prediction of the risk of the acute kidney injury, and we demonstrated with integrating of both type of features, we can achieve a good performance. So this is essentially one of the multi-model / multi-view learning stuff we have done. And this is another example where we have electronic health records, but at the same time, for certain diseases, like in this case, is Parkinson's disease. So we also have longitudinal image scans. Like in this case would be the DTI scans, diffusion tensor imaging longitudinally. So how can we, process the two type of information and then come up with unified predictor or classifier in this case to diagnose if this patient is having Parkinson's disease or not. So that's kind of like a classification problem. So we use a memory network type of architecture with two pipelines. So one for processing the longitudinal electronic health records, the other for processing, that's a graph neural network to process the brain network, and then combine them all together to come up with a classification, and it achieves a good performance in this case for Parkinson's disease classification. And another important information that we want to leverage in a limited sample size case is the domain knowledge. And the domain knowledge is typically encoded in either, by the domain experts, you want to keep the human in the loop, or it is documented as text, like in the papers or the books, or whatever guidelines. So we have to do literature mining, and this is actually a challenge we participated. That's a NeurIPS challenge in 2017. We do literature mining to classify the clinically actionable genetic mutations, and we win the challenge. And this is kind of like the pipeline we did. And in my lab, we also built this integrative biomedical knowledge hub, which includes like over 2 million biomedical entities, over 50 million relationships, and it is publicly available. If you want to use that, you can use knowledge graph embedding, whatever technique, to kind of come up with some embedding vectors or learning whatever as a pre-training, pre-trained embedding vectors for those entities that can help you to improve your algorithm performance. And this is another example we have done, like a mutual enhancement between the biomedical knowledge graph and you know the data-driven predictive modeling, like using electronic health records, because as I said, we can use a biomedical knowledge graph to come up with better pre-trained you know, biomedical entity representations to improve your predictor. But at the same time, the biomedical knowledge graph could have noise, could be incomplete. So you can also use your data-driven inference, I mean, from the electronic health records to improve the quality of your biomedical knowledge graph. So I mean, you make this a closed loop, so you can do like this mutual enhancement to like improve the performance or the quality of both your you know, EHR built predictor and you know, the quality of your biomedical knowledge graph. And of course, another important thing is if you, that's all about the features or integrating the knowledge. And if you want I mean, better interoperability, like you want your model trained on one EHR system to be able to apply to another EHR system, you need some sort of standardization. This related to the you know, standard or you know, like unification. I mean, building common vocabulary to like standardize all the EHR terminologies. So we have done some FHIR related. That's interoperability standard for transmitting the electronic health information, and we have done some work on that as well. Of course, if you want to like securely integrate the data from you know, different local institutions, you can you know, one popular technique is federated learning, and with the COVID-19, there are several papers on major journals because we really want to leverage data broadly, but we don't want to share the raw data because of security concerns. That's how this federated learning is raising more and more attentions in the biomedical field. And this is Nature Medicine article published recently, and we have also a perspective piece pointing out the importance. And this is a paper we demonstrated on 5 hospitals in Mount Sinai using federated learning. We can get a pretty good performance. It's compared to the pooled. I mean, what if you assume all institutions can share their data? I mean, we can achieve you know, comparable performance. So that all those demonstrated the potential of federated learning. And of course, there are still a lot of, I think the application of federated learning in biomedical field is still pretty limited. I mean, people are still testing the most standard strategy, how to handle like the heterogeneity across local sites, and how can you like you know, design effective collaboration strategies is something still missing. So there are still lots of opportunities on biomedical federated learning. And yes, this is another related paper, which is swarm learning. I mean, because in federated learning, you have to transmit model parameters to a central server, and then you update model parameters and then transmit back, and transmit those model parameters can leak information. So these folks, they think about build a blockchain to, you know, instead of having a central server, but have everybody build a smart contract using a blockchain architecture to update and share the model parameters to make it more safe. And they also added differential privacy on top of that to further guarantee the security. So actually, we have done something similarly as well. So where we I mean, think about, rather than a blockchain, we really think about in a decentralized asynchronous scenario. So how can we add differential privacy into the model parameter updating process to make sure, I mean, everything is secure, and the paper was recently published on PAMI. Those are like on the data aspect, on all the model aspect, because we have you know, small and large piece, so we can have this model under specification problem. So it is different than a model overfitting. A model overfitting is you don't want to I mean, your model behaves too good on the training, but not good at testing. But typically, your train and test are from the same data. So model under specification is if your model, I mean, it has learned from one data, but it not necessarily behaves well on another data because of the potential data set drift, because the small and large p, type of setup. So that is not surprising. And there are also some clinical papers pointing out, I mean, the model, learned from one place does not work well on another place. It cannot be reproduced or something like that. I mean, all these things, it doesn't mean the original paper, the authors, they are cheating. It's just really, I mean, you cannot guarantee in most of the healthcare scenarios, you learn the model well on one data set, it does not necessarily mean it can work well on another data set. So this is just because of the large problem space, small sample size, and also large dimensionality of the features. I mean, all these things can happen. It's not surprising at all. It's just how can we make these things, I mean, mitigate these things and give the model more credibility, and how can we make them more applicable to different places. Of course, one way to do that is you never want to just blindly deploy a model trained from other places to your current data set, but you may want to do some transfer learning, fine-tuning, adaptation stuff. So we have done, I mean, one work that is based on meta learning. Meta learning, everybody knows it's essentially effective. I mean, the goal is effective and efficient fine-tuning, right? Hopefully you got a better set of model parameter initialization so that it can quickly adapt it to your optimum model parameter setting based on your local data set, and it works well. I mean, in our case would be Alzheimer's disease risk onset prediction. And this is another work we have done recently. I mean, we predict suicide risk, which is a rare event, and with a local hospital data, I mean, you wouldn't have enough sample size because suicide event is so rare. So how can we leverage a large external state level, connected state level database where we kind of like using patient similarity as a link to borrow some of the similar patient information from the external data as additional predictors in my local suicide risk predictor to enhance the prediction performance. And I think another, of course, not surprising phenomenon people have observed and studied a lot is bias. So because small and large p's, a lot of the times you cannot guarantee because you don't have large enough samples to characterize the data distribution across different groups. So you may suffer from different model performance on different groups. So that's the bias problem. And there are, of course, lots of fairness adjustment either intrinsic or post hoc strategies proposed in recent years in machine learning literature. So one thing to consider is when you adjust the fairness, you don't want to lose your model performance because if you just care about fair and at the same time your model performance drops dramatically, essentially the model is useless as well. So this is a recent paper we have done using dynamic programming to consider both the model performance as AUC and also the fairness measured as delta AUC. So it can achieve a fair adjustment, but at the same time doesn't lose too much on the model prediction performance. And of course, another related topic is interpretation. So we want the model to be interpretable. I mean, we have some recent paper. I think I'm out of time, but I just go through this quickly. So, I mean, for model interpretation, so there is intrinsic, there's post hoc, and one important issue to consider is whether the interpretation is reliable, or in this case, stable. So like LIME is, I think everybody is familiar with, it's very popular, but because of the random nature when you do the interpretation. You have to do random sampling. I mean, it may make the interpretation unstable, so we further enhance that with some statistical testing. So unless it satisfies the statistical significance, we're going to increase the sample size to improve the stability. And of course, another thing is we can measure model disparity, but can you figure out why that disparity happened? So that's explaining algorithm disparity. For the sake of time, I wouldn't explain that in very detail. But this is like essentially a causal mechanism that explains that, I mean, leverage SHAP, which Dr. Zhou just introduced, but we really decompose, the disparity on the different decision paths, causal paths on the PDAG. So it is not just attribute to the features. Of course, the last thing is in federated learning, how can we consider both performance and fairness? And this is actually a recent NeurIPS paper we published, how to consider both in federated learning, because currently not too much federated learning strategy considered fairness. So I think I'm over 1 minute over, but the conclusions. So I mean, we have to realize the difference of patient health data analysis compared to those conventional computer science scenarios, and we have to be mindful about the scenario and lots of important directions, including multimodal learning, model under specification, fairness, and interpretability of federated learning, and so on and so forth. There could be more. So, but the core is how can we make machine learning model work in this small and large P scenario? So with all that, this is my collaborators, my team members I would like to acknowledge, and funding agencies. And as I said, so this is just like a brief overview of a lot of the works happened in my lab. If you're interested in hearing more or knowing more details, of course, you can send email to me, but I'm going to give a short course, a 3-hour short course in the New England Statistics Symposium in May. So you are welcome to attend as well. And this is my email and webpage. And thank you. I don't know if we have time for questions.
Great. Thank you so much for the great talk. And yeah, so if anyone has any questions, feel free to ask. All right, so if no one has any questions, so maybe we can just take the lunch break.
Hello?
And yeah, go ahead.
Can I ask a question? Okay.
Sure.
Hello, Professor Wang. I'm a PhD student in Illinois Institute of Technology, and my advisor is Professor Kai Su. And I'm very interested in expandable AI, and I think could you have some comment on how to utilize explanation for debias, maybe?
Explanation for debiasing?
Yeah.
Yeah, I mean, if you send me an email, I can send you my paper. I mean, in last KDD. So what we did is, so first, those debiasing methods. So first you have to come up with some quantity to measure that disparity, right? So you can use, for example, the equal opportunity or equal odds. You can use, what we use is a delta X AUC. And then with that quantity, it's similar to AUC, right? You can use, let's say, techniques like SHAP to decompose or attribute that disparity to potential causes, right? So of course, if you think about the potential causes to be features, you can do simple, the most straightforward SHAP, so that you know which feature contribute how much to the disparity. But that a lot of the times, single feature is not enough if you talk about explanation. So what we do is we first build a PDAG partial unidirectly acyclic graph, so you can see the causes of that potential decision path, and then you use SHAP to attribute your disparity to those decision paths. So you know, like if you're following this path to make the decision, or if you're following that path to make the decision, what is your amount of contribution to the disparity? And then you can also similarly look at what are their contributions to the precision or the accuracy. And then if there is certain path contributes a lot to disparity, but not too much on the to the accuracy, you can eliminate that, right? So that is kind of like a really transparent and actionable, like a debiasing type of way. So that's what we did. Yeah.
Okay, I will read the paper. It's very interesting.
Yeah. Sure.
Okay, thank you.
All right, I think that's it.
All right, sure. So we can just take a break for 1 hour, and we're going to come back at 1 p.m. in Pacific time. So yeah, I'll see you guys then.
Thank you.
Thank you.
Hey, Ramtin. So thanks so much for inviting me to speak. Is the screen visible?
Yeah, thank you. Yeah, it is. Yeah, I can see the screen and I can hear you very well.
Okay,
so
great.
Let's get it started. So welcome back, everyone. So our next speaker is Professor Madalena Figueroa, and who will be presenting in increasing trust in Alzheimer's disease forecasting. Ina completed her PhD in machine learning at Carnegie Mellon University in 2015 and was a postdoctoral fellow at Stanford University. She joined the College of Information and Computer Science at UMass in 2018, and her research revolves around hybrid methods for multimodal data, especially data from the healthcare domain. Ina, we're excited that you're here, and please go ahead and start whenever you're ready.
Thanks so much for the invite and for that kind introduction, Ramtin. So yeah, today I'm going to talk about how to increase trust in Alzheimer's disease forecasting. This is work done in the InfoFusion lab, my lab at UMass Amherst, with my students Sidong, Jia, Yiren, Evan, Gunlin, and James. Some of them might join this call later today, so give them a shout out if you see them. The research is supported by the Manning-Iles Innovation Award. Right, so let's begin. So Alzheimer's disease. Alzheimer's disease is the most common form of dementia. People with this condition experience progressive cognitive impairment, disorientation, and memory loss. And in addition to all of these symptoms, they and their family members typically suffer from mental pain, burden of care, stress, and depression. Now, statistics reveal that approximately 44 million people across the world live with Alzheimer's disease, and AD is one of the leading causes of death in the aging population. So obviously, this is a disease that we'd like to cure or at least forestall if possible. Unfortunately, the painful truth is that despite years of clinical trials, there's currently no cure for Alzheimer's. And the images here show how Alzheimer's affects the brain. So this right side image that I'm pointing to right now is a PET scan. So we see that by the time of AD diagnosis, as much as 60% of brain matter is already lost. So there's not much that can be done about it at that point. And here we have an image of what a normal brain would look like versus a brain with Alzheimer's. So it's just a figure, but basically it stands to reason that some of these changes that are so drastic at the time of diagnosis would be visible on brain scans sooner, and would thus be able to diagnose the condition earlier by looking at the image. So looking at this patient historical data and their current status, we'd like to be able to detect Alzheimer's in the very early stages. And that's because this would enable clinical trials, and also it would allow people to plan ahead and have a better quality of life. Now, the time intervals that we're looking at are on the order of years rather than months. So there are a number of apps that claim to be able to detect Alzheimer's, like some claimed 10 years in advance from behavioral data. And we recognize that behavioral data is important as well. I will point out the studies in these apps are based on report accuracy rather than F1 score. And the diagnostics labels themselves are not very precise. Basically, the subjects are not really tested every 6 months as subjects in a clinical trial would be. In any case, for the purposes of this talk, we'll focus on clinical data from longitudinal studies where the diagnoses are unambiguous. Okay, so the question is, how do we build a trustworthy Alzheimer's forecasting model? Well, let's see what trustworthy machine learning is. And according to trustworthyml.org, trustworthy machine learning consists of machine learning models and algorithms that are not only accurate, but also explainable, fair, privacy preserving, causal, and robust. So all of these characteristics make up a trustworthy machine learning system. So they're all kind of pieces of this puzzle that make up a trustworthy machine learning model. So let's see how we can get there, or how far we are from the ideal trustworthy machine learning system for the purposes of Alzheimer's forecasting. So let's go back at the original goal. Our first attempt is to basically increase the accuracy, because that's kind of a precondition for a model to be trustworthy. So our original aim was to have a model that looks at the brain image and all of the other patient information and tells us what the health status of the subject will be months or years down the line. So here we have like kind of a depiction of that type of model. The idea that we put forward that proved to increase accuracy in our case was to learn an abstraction of the patient's overall status and use that information to predict the next abstract status, which is in turn used to determine the disease label. So we have that abstract representation of the health status, which changes at every point, and it sort of comes from the previous representation, and it is used to map the disease label. So what we've done here is decouple the transition predictions from the output classification, and in doing so, we have our deep learning model operating a bit like an HMM model. What we use for this study is data collected from the Alzheimer's Disease Neuroimaging Initiative. And this kind of slide shows all of the data that was collected as part of AAAI. And here the bolded text indicates the information that was collected. So things like demographics, vital, diagnostics. And the latter includes MRI and PET scans, which we're going to use. The shapes, all of those triangles, squares, etc., indicate what was collected and in which context. And what we can immediately see is that the information collected is irregular, and some information is collected in some visits, but not in others. And also the collection protocol changed over time. So it's why we had AAAI 1, 2, 3, and AAAI Go. This data includes structured information, it includes time series images, and these were collected at screening, at baseline, and then every 3 months, and finally every 6 months, and then yearly. And this heterogeneity is important because of this heterogeneity, because of this characteristic of the data, every single study that works with this data has ended up needing to select a clean or manageable subset of the data. And the consequence is that this results in a number of inconsistencies across studies. So it's really difficult to compare numbers. And we'll come back to this aspect later, because it is important from the trustworthiness perspective for things to be replicable. So for our work, we chose to operate with MRI scans, cognitive test scores, and biomarker information. And because the data is collected as part of AAAI, the privacy preserving aspect of the trustworthy ML model is somewhat solved via the data collection process. So users should not necessarily be tracked through their collected data. So ADNI supposedly ensures that. We will revisit this later as well. But for now, let's accept that the data is held securely. All right, so let's talk about our Alzheimer's forecasting experiment with the ADNI data. So we used 658 patients in total. And in this figure, we show the class balance information of the data that we used for our experiments. So the numbers over these arrows represent the number of transitions from one disease stage to another within that data set. We used visits 1 through 5, so patients that had at least 5 visits. And for this, we use the image features, the structured covariates, the cognitive test scores. And we had information from L visits. So this XVI information is the data from visit I. So all of the data that we would have at a visit I. And of course, the visits are ordered according to the time when they were collected. And the task is to predict the disease stage tau visits into the future. So let's see how we can do this with a baseline model and with our own model. So with a baseline model, we use a simple or a standard RNN here. So the visit information is provided to an MLP, which computes some embeddings of all of this information. And on top of the embeddings, we have an RNN model that appends the forecasting window and has this disease progression classifier that provides the label tau visits in the future. So that's the baseline. Now, this is our own model, FLAIR. So it also uses an MLP to extract some embeddings. And these represent basically the health status at each visit. And then an RNN operates over these to capture the temporal dependencies, same as for the baseline model. But the difference between that and FLAIR is that we have the second MLP, which maps from these sort of encodings back to the health status. So we have this component that tries to forecast not the label, but the health status itself, that embedding of the health status. And whenever we have future visit information, we actually compare our predictions, so these F hats, against the true embedding of the patient information from those visits. And we actually look at how well we can do this forecasting by including a loss of by including the difference between the forecasted health status and the actual health status in our objective function. So through this procedure, we're able to essentially forecast health statuses several windows ahead of time, and then finally map that last health status, the one at visit VL plus tau, to its appropriate label. All right, so that's how the model works roughly. So let's look at the results. So here we have the FLAIR model in orange versus the baseline in blue. And on the x-axis, we have the number of visits in the training data that's actually used to train on. So if we have 4 visits in the training data, the forecasting window is going to be only 6 months. We see that FLAIR performs a little bit better than the baseline model. And for 12 months, again, FLAIR performs a little bit better. But we can see that the real gain here is for the 18 months forecasting window. So our performance is a lot better. And just remember that this is a 3-class label problem. So we're trying to distinguish between Alzheimer's, MCI, and cognitively normal. These results were presented at Machine Learning in Healthcare in 2019. So we can see that here we have a reasonably accurate model. So we have basically our first kind of piece of the puzzle, the precondition to making a trustworthy machine learning system for Alzheimer's forecasting. So let's talk about how to introduce causality into this. So basically, we'd like to consider the causes and effects of Alzheimer's. So we've seen that causal models from the machine learning perspective ideally would introduce something like causal inference or counterfactual reasoning. And we have seen models like that in Utah from earlier today. Now, for the purposes of this application, when we say that we'll look at causality, we'll take a more casual view of causality, and basically we'll consider the known causes and effects of Alzheimer's and try to use this kind of known causal graph to introduce better features in our model. So from domain knowledge, we know that there are some genetic predispositions to Alzheimer's, which are encoded in this APOE gene. Now, this in turn causes deposits of the amyloid and tau proteins. So the research is still ongoing as to which of the amyloid and tau are cause and effect. So nobody knows exactly whether it's amyloid causing tau, tau causing amyloid, or something in between that happens. But the case is that the buildups of amyloid and tau in the brain are sort of what causes ultimately Alzheimer's. So it causes these structural changes in the brain, and it also causes the lack of physical activity. And it also causes things like confusion and aggression in subjects. So this is roughly how the cause and effect looks like. So obviously we'll have to consider genetic information, and obviously it'll be a good idea to look at structural changes in the brain. And on that note, let's look at what a normal versus an Alzheimer's brain looks like. So these are basically the effects of Alzheimer's, but they could be potentially identified early here. So these MRI scans that are present in the ADNI data can capture very relevant anatomical information, though it's really up to us to extract relevant features from the MRI. So first way to go about it is to use the observations of neurologists with respect to the tissue shrinkage that actually occurs in the brains of people with Alzheimer's. So some key regions that are affected are the hippocampus here, which is vital in the formulation of memories, the cerebral cortex shown here, which is involved in thinking, planning, and remembering. And finally, these ventricles, which become enlarged and fluid-filled. So our idea is let's try to incorporate images into this disease forecasting. But how to extract relevant features from these images? Well, it turns out that people have been using the MRIs for AD diagnostic, and will sort of take a take a side road here and look at a few AD diagnostic models, and let's see how those manage to actually extract relevant features for this problem. So usually in these studies, they use the neural networks to actually featureize MRI and assign labels. So there were a number of 2D models and 3D models that use this MRI data, and they reported incredibly high accuracy. Notice here that the number of subjects changed between studies. The number of MRIs used also changed between studies, and the accuracy was really high. Well, so first of all, this is accuracy, not F1 score. So because Alzheimer's is rare, there could be an overestimation right there. And then there's another issue. How much can we trust these results, since we are talking about trustworthy machine learning? Well, let's look at an example of how these disease stages for a patient are captured in the data set. So a patient starts out as cognitively normal in the initial visit, and then the subject might progress to MCI, and then finally to Alzheimer's. And some subjects, actually a lot of subjects, don't really change at all. And in terms of splitting the data into the training and testing pools, the ideal way to do this is to split by patient. So basically put the MRI scans from all the visits of a subset of patients in the training data and the MRI scans from all the visits of another subject of patients in the test data. And there should be no intersection between the two sets of patients. So that would be the ideal way to do it. We have some patients in training and some patients in test. Well, it seems like these studies took different approaches. So some basically split the patients by visit. So they essentially put the first few visits of patients in the training pool and the last few in the test pool. Which I suppose it's fine if you're assuming that you can do a personalized model and that you will have MRI data for the subject for which you're trying to predict. But this is only applicable in a limited number of scenarios, because usually when a subject comes in to get their brain scan, you're not going to have their historical information. Another thing people did is they basically split the data from the MRI. So you could have the case where future data, so data from the later visits ends up in the training pool, and data from the earlier visits ends up in the test pool. So obviously, if the subject was cognitively normal throughout, then they're not going to change. So that's basically cheating in the model evaluation. We essentially did a replication study to see how well these models actually behaved when tested on kind of a fair in a fair evaluation framework. So these were the subjects for which we tested the models. So we can see some are MCI, AD, cognitively normal, and there are some transitions right there. We noticed that there are few transitions to actually train on compared to with the number of subjects that we have. And this is our basic pipeline. So we tried 2D ResNet and 3D ResNet models. And these are basically the results of our replication studies. So we noticed that when splitting by patient, every one of the networks that we tried on, and these are documented in our archive paper, and which was also shown at the ISHCAI aerial workshop. Basically, the split by patient revealed that these models aren't really learning any useful features that could be transferable. They're actually just memorizing patient data and making predictions based off of that. So we can see that if we split by visits or split by MRI, we get good performance. But that's basically a gross overestimation of what those models can achieve. We also realized that this puts in question whether the data is indeed privacy preserving. So you have the very clear risk of brain data essentially being memorized in the network. So allegedly, you could re-identify a patient based on their brain scans, which is very troubling. That really explains why the performance is so different, because the model just memorized someone's brain. They know they're cognitive normal, and they're just going to predict the same label onwards without the transition. So we've basically learned that these deep models are simply nowhere near good enough at automatically extracting features for Alzheimer's diagnosis. So at this stage, they won't suit our purposes for AD forecasting. And learning good features from these MRIs is still something we're working on. I will point out that there was this one study from Narges Razavian's group, which was shown at the ML for Health Neurics workshop, which is replicable. So their network was able to obtain basically a balanced accuracy of 70%. So we were able to successfully replicate these results, though unfortunately it's still not enough to say that we can automatically extract data from the brain. Instead, we will use that causality kind of graph that we have and use already existing features. So we're going to use the genetic information. We have that in there. And we have volumetric features that are already pre-computed, like the volume of the hippocampus. So we will rely on those. And as a bonus, the model becomes more explainable because we have used these features. It's not 100% explainable because we still have that RNN operating on top of it. It's definitely more explainable than if we had pulled features using those large-scale convolutional networks. These are basically the forecasting results with different features. So here is when we only use the cognitive test scores present in ADNI. This is when we add the genetic information. The orange is when we add the genetic information. And finally, the blue is when we add everything. And on the x-axis, we have different forecasting windows. So we can see 12 months, 18 months, and 24 months. That kind of wraps up the sort of feature kind of integration study, and this gives us like another piece of our puzzle that leads to the construction of a trustworthy machine learning model. And I'll talk about improving model robustness for a bit. So this was our basically learning curve on the validation set with the original FLAIR model. We noticed that there were these instances when performance looked really good on the test. It's not shown here, but basically on the validation set, you had these dips. So what we did to correct this is actually use parameter freezing for some parts of the FLAIR model. So in stage 0, so epoch 0 to 10, we didn't freeze our model at all. And then in the next 20 epochs, we froze the MLP in the red circle. And then in the last 20 epochs, we unfroze the MLP mapping and froze the rest. And with this parameter freezing, we actually improved the robustness of the model considerably. And basically, this is important because as this is validation data, improving this robustness means that the results are more likely to translate well to other data. So this basically makes our model more robust as well as accurate. And when tested on a 24-month window, we noticed that the performance remains high. So we're getting an F score of above 0.8 now. So we can see that by improving robustness, we've also managed to support an improvement in accuracy. All right, so let's now discuss whether fairness can be ensured for this application. So in the ADNI study, unfortunately, there are very few non-white participants. So these are sort of the numbers of a subset of the ADNI data. And we see that the proportion of participants that aren't white is very low. So to put it simply, it's impossible right now to accurately ascertain whether these models are high performing for these racial minority patients. So to be fair, we basically need more data. To even assess whether the model performance is good enough, we need more data. So just to recap, we've essentially shown that the models can be fairly accurate, can consider the causes and effect of Alzheimer's, can be made robust and have some degree of explainability by using pre-computed features. We've noticed some issues with some potential issues with the privacy preservation part of the data, and fairness has not been done at all. So that's where we are in this process. And eventually, if this is successful, if we can accurately forecast Alzheimer's, this will be useful in selecting subjects for clinical trials. So we'd have a sequential screening process based on at-home monitoring and in-hospital tests to actually get a clinical trial cohort and subject those folks to some medication to see if Alzheimer's can be cured or forestalled. I will give a shout out to the new Mass AITC Center. which was just funded at UMass Amherst. I'm not affiliated with this, but it is at UMass, and there will be a number of positions available via the center. So those of you interested in Alzheimer's, definitely check it out. There are going to be some fellowships available for those of you that are going to be on the job market soon. So this is just the acknowledgement for the AAAI data, which is great. And thanks, of course, to my students. Thank you so much.
Thank you so much for your great talk. And if there's any question, please go ahead. Yeah, I can see a few questions. So Monica. So Monica can go ahead and ask.
Hey, sorry, that was just a clap. It wasn't a question, but sorry. Hi, nice to see you.
It's great to see you again, Monica.
Yeah, great talk. And no, I do remember like we were talking about this idea while I was at UMass. So it's really nice to see you here again.
Thank you.
I have a question.
Yes, please.
Hi, Madalena. Thank you for your talk. It's actually really relatable to some work that I'm doing. I wanted to ask you about the kind of study that you had done on other baselines where you saw faults like, okay, they weren't splitting the train set and the test set properly. What other kind of problems do you see currently? Because I was doing that, and then my professor told me, okay, Rupali, you got to split the data like based on something else. So what I did was I split the data set based on a date. So it's not necessary that for one patient, let's just say some part of it would be in the train and some part would be in the test, etc. I did it by date. Do you see any problems with that? Or I don't know, do you see any other problems?
It depends on the deployment setting. So if you split the data by date, you're automatically, and you put, so you obviously you should have the past data as part of your training set.
Yeah.
There's no instance where it makes sense to have your future data, your past data in your test set.
Yeah.
You are automatically making the assumption that you will always have data from that subject in the training set. So if you have a new patient that comes in, for that model to behave the way you expected, you have to basically retrain the model using that person's data in your training set. And there is a very clear risk that all the model actually does is it memorizes characteristics of that patient, and it just feeds you back like the diagnosis from that patient's like prior history. So that's why it's very important to look at transitions, right? Are transitions captured? Are people that transition from cognitive normal to MCI and from MCI to Alzheimer's, or whatever condition you're working with, are they handled well by the model?
Mm-hmm.
Because in this case, what we've noticed is the model was just memorizing brain data. They saw the same brain, they gave the same diagnostics. And because a lot of people weren't changing at all, it seemed to be going great, but it wasn't.
All right. Okay. Well, I am presenting my poster in the next poster session. It would be great if you could come visit and tell me what I'm doing wrong. Thank you.
Well, I'll have a look and give you my opinion. I'm sure it's great research. All right. Thank you so much.
All right. So if there's no more questions, so we can just go ahead to our next invited speaker, which is Professor Wei Wang, who will be talking about mitigating bias in medical data. Dr. Wang is a professor in computer science and computational medicine at UCLA. She received her PhD in computer science from UCLA as well. Dr. Wang's research areas include big data analytics, data mining, machine learning, NLP, and also computational medicine. So Wei, we're excited for your presentation. Please go ahead and start when you're ready.
Can you guys see my screen yet? Or no?
Not
Let
yet.
me, how do I do this? Apologize, this is a new computer for me.
Right.
I have to quit and rejoin this in order to enable sharing. Sorry, I'll be back.
Sure. Yeah.
Right now. Okay, let me share again. Hopefully. Now you can see it, right?
Yes, perfect.
Okay, wonderful. So today I'm going to share with you on one project we're doing, and then I picked the title, say, well, we did consider some data bias in the system when we process medical data, but this is kind of an ongoing project, right? So we don't have a final solution, but I just want to share with you some of the thought we have, some of the things we have tried, and the approach we are taking. I appreciate if you can give me your feedback and see, well, whether you think certain things could work or not work. So there are many potential bias in the medical data, especially in the medical data, right? So because typically, if we look at the clinical data, like from real patient, right, not simulated data, and then often the case, like, it's quite a complex demographic distribution of those patients, right? We cannot control that, right? So most of the clinical study, if you talk to them, they try to select a cohort that more or less a little bit uniform, maybe in one cohort, like all male or all female, or between certain age group, or they control the distribution of the ethnicity. They want to have some control. But if you say, well, let's not do that, let's just look at whatever the patient data in the hospital, because I'm working with like UCLA hospital, which has like a few millions patient record, right? So we can't really control for that unless we want to really drop a lot of data. So we basically have to handle this, and also the data heterogeneity is huge. Often the case, right? If you look at EHR data, it's have multiple modality, right? So it depends on what the patient have been through, and there will be some lab result typically, and then some clinical text typically, right? And then somebody maybe with images or like procedures or other type of, it depends on like, what the health condition the patient is, right? Some of them you have like maybe a more complete patient history, and for some you only have like maybe one visit or two visit. So there's a lot of missing data. And also if you look into their EHR data, I think that it's also some of the patients, you have a lot of data, right? A lot of information there, and some of the for some patient it's very sparse. So even when we zoom into like clinical text, right, the doctor's notes, and then it's not even uniform because they're written by different people, right? So they have somewhat different style, and some of them are very long, detailed, and some of them are relatively brief. So there's a lot of non-uniformities there. that's just reality. And we want to be able to find a way to handle that. So somehow, can we harmonize this to some extent? So that's what we have been thinking. So we want to build a unified representation of medical data so that we can do better job in like data cleaning, imputation of missing data, and de-bias, right, for whatever bias there, and then to normalize the data, and such that we can do better query answering, right? So if we want to search for similar patient, right, patient with similar profile, how do we do that? And can we do inference, right? Can we do prediction? Can we do ranking? So we want to somehow massage the data so that it can better help us to do those, right? And then we also realize the importance of existing knowledge base. There's a lot of existing knowledge base, right? Not in a single location, but distributed like in many different locations, maintained by different people, different group, focus on different aspects. So we want to be able to leverage that. That hopefully can help us during the process of, de-bias, during the process of imputation, cleaning, normalization, query, inference. So our system would want to be able to bring both the data and the knowledge together to see if we can do it in a more uniform way. So in order to do that, we propose to use graph as a unified representation. So the reason we choose this is that graph can represent a very rich context, right? So we all know graph have nodes and edges, and graph can be attributed, so you can associate that with each node with as many information as possible, as many attribute, text, image as possible. And also the relationship between those events, the node can represent the event, can represent the patient, right? So, and then between those things, like they have also complex relationship. One type of relationship we focus a lot is the temporal relationship, because it's very critical in modern patient trajectory. So we have 3 levels of those graphs. We have graph representing all those individual patients. It's very detailed. And then we also have something called the instance graph. So that was a case graph. Instant graph, basically we want to be able to aggregate across multiple patients, especially if they suffer from the same disease. They are not the same, but we want to be able to distill what's common across them, right? So to build somehow a knowledge representation of that specific disease. And also we have the next level, is called concept graph. Those are basically existing biomedical knowledge, ontologies, right? Things we could derive from literature, so all of those. And all these 3 types of graphs are connected. You can think of there's a 3 different levels of granularity of how we describe things. And then we want to use graph representation learning to hopefully to be able to learn to map this into latent space. And in that latent space, we could do better like denoising, de-biasing, normalization, imputation. So this is a excuse me. This is example like what a graph we have envisioned at the basic level, at the patient level, right? So you can see this depict a patient's trajectory. Excuse me. Sorry. And this we derived this from a clinical case report, actually. So you can see this model's different timeline, the different time point, and the procedure the patient has been through, the symptoms the patient is experiencing, and whether what the observation that the doctor makes and the final diagnosis. So this is very typical, but for different patients, you can imagine this graph could be very small or very big. So having that, right, so this is just one type of data we want to incorporate, but we have other like imaging data. We have other like nowadays more and more patients are like maybe going through like some genetic tests, right? So there's some protein biomarker tests. So all of those data we want to be able to model. And so basically our goal is to be able to actually to integrate all of this together, not as a separate pieces, into a more uniform way of representation, uniform representation, But we do have to address these challenges I just mentioned. And this is actually has been our focus. We use a lot of technology, for example, NLP, semantic analysis, image processing, a lot of those things, and also graph representation learning. So to to process data, to be able to generate like, you know, a more cohesive piece of knowledge. So this is the overall architecture of our system called the BioCare. And so sorry, because I have an allergy because it's a springtime. And so I don't want to like overwhelm you with all this different, detailed architecture, but basically the idea here is that we process the text data, right? So through anti-recognition, relation extraction to map that into a knowledge graph, right? So this could be either case graph, instant graph, and then connect those knowledge graphs with this, you know, like ontologies, external knowledge base that's called corresponding to concept graph. And once we have that, we do representation learning, but we don't just create one latent space, but actually multiple latent space. I'll talk about later, so that to better fit our need. And through that process, we do normalization and the debiasing. Okay, so this is, you can see that the three types of the graphs, and right, I don't know if you can see my cursor, there's a normalization and alignment, and then to make sure that everything's inconsistent with each other, and then we actually try to remove some type of a bias from the data. So a little bit like what we do, and then so you can see that this is one example of like how do we extract, so map this text in onto a knowledge graph, so that you can see this highlighted in different color. That's different different entities we extract. It could be event, could be symptom, could be, you know, there's actually we identify 24 type of entities we want to extract, and all those links, the errors corresponding to a relation that we extracted. So this is done automatically. So so this would be like what the graph may look like from that piece of text, and then you can see that it's a you know, very detailed description of the patient's patient trajectory. And through this step, we hope that at least they will, like, you know, filter out some of the irrelevant information and some of the noise from the data, and make a patient more, you know, comparable across each other, right? Because otherwise we can't really directly compare one piece of clinical text to another piece of clinical text, right? So it's hard for us to do the, you know, similarity match, right? We can't do like word-to-word match, right? So we have to somehow learn what's the semantics buried in the context of this clinical notes, right? To have a better understanding what the patient's you know, trajectory is. So this part, I mean, identify those. So we rely on like enabled entity recognition, and then this is a standard platform for that, right? Neural network architecture. So so we did like, you know, on top of this later, I'll show you that, you know, to make it perform better. So this is just a standard one. And so this is actually, I took this from our paper just to show that, you know, this is, even this part is ongoing work, right? So, and then it's not like, you know, 100% accurate. So this is a quite challenging task by itself. And sometimes depending on how difficult the task is, then the actually the F1 score could be as low as like 65%. Okay, but most of the time actually it's not that low. So we just show you that it's it depends on how detailed information you want to filter out, or you want to extract out from the text. So another important task in this thing is really the relation extraction, especially temporal relationship. And so from this piece of text, you can see that, you know, this is a very short piece of text, but convey very important information. And in the graph here, it really shows the temporal relationship between different events. And so you can see that, you know, this arrow indicating that this A is before this B, right? So, and then this, the one without arrow is basically they happen simultaneously or at least overlap. And it's hard to determine like which one is exactly a little bit before the other, right? Because sometimes there's only exists like a partial order. So this is, you can see sometimes like it's easy to extract, like if they explicitly mention like a day later, right? Sometimes it's implicit. You can only infer the relationship, so that we do both. The way we do is that we want to use a temporal relation. Basically, we use the probabilities of logic to encode this temporal relationship, and then using this as a constraint on the neural network model to do better inference. So you can see that this last column is our model, and then this does a lot better than, you know, alternative approaches in terms of extracting and infer temporal relationship. Because a lot of those implicit temporal relationship we want to infer, right? All those explicit ones are almost 100% accuracy. It's just those implicit ones, how well we can do. So you can see that, you know, after these two processes, this is what a patient would look like. And this figure I'm showing you, I apologize for like, you know, look very messy, but this is the outcome of our system from like a real piece of text, a clinical text, and to derive this. Okay, so you can see that it's already quite detailed information. We hope this can be can represent as a better way, a more uniform way to represent the patient, so that they will be not so much biased, you know, against a certain group of patients. But of course, there's still bias exists. You can see maybe some of the, I only show you one patient, but some patients actually this graph is very small because it doesn't have a lot of information. Some of them is very detailed. And also in some part, like maybe, you know, there's some missing data, right? Because one of the observations we make on this, especially clinical data, is that when the doctor wrote the note, right, they only write down things they feel important, especially things they consider abnormal, right, that can explain their, you know, diagnosis or justify, right, the treatment or the exam, the test they want the patient to go through. If for other things, they may decide not to write, especially things are within the normal range, right? So in other words, when the medical record lack of certain things, description of certain things, it does not necessarily mean the patient do not have it. That only means that that doctor is not the focus of that doctor at that moment. For example, that could even mean like some other disease, right? The patient suffered, but unrelated, or the doctor believes that's unrelated to the current symptom. The doctor may not say it at all because they don't think that has any connection. So you can see that there's a lot of those kinds of missing data that we need to handle. So the model, which means the model cannot assume, you know, what's not present there are always negative, right? So it only means like it's a lack of information. So that's, we need to be very careful when we apply the machine learning model on this type of data. So after that, you know, I mentioned that we want to incorporate other existing knowledge base, and there's many of those existing knowledge base already well organized, but they are maintained by different teams. They may not be 100% compatible with each other, right? So often the case we retrieve those integrated knowledge base by some ID system, right? They use, and for example, you want to link to like ICDs, ICD-10, or you want to link to like disease ontology or drug bank. So you will always need to rely on some ID system. And when you start to look at that, you know, there only have partially linked in some way. So not everything is completely mapped well with everything. So there's a bit of work we're doing here is to actually, how do we harmonize this? And so in our system, actually, for example, all the symptoms, as long as it's recognizable ones, it's already linked to the if there's a corresponding ICD code, or if there's corresponding symptom described by the disease ontology, for example. So it's already linked. If there's a medicine being used, we also link it to to its own ontology. So there's a lot of, you can see there, there's this more or less a flat, this patient graph, but on top of that, there's this hierarchical ontologies, that multiple of them, many of them there, so that to help to link things, to provide the context, because otherwise, if we say, oh, this patient has a fever, right? So fever is just an English word, right? And then without supplying the additional medical context of this, the machine learning system is very hard to link that to certain disease. Okay, so it's only when we bring in the medical, knowledge that we can somehow start to make sense out of that. So this is what some ontology would look like. It's typically it's a hierarchy, right? So you can, there's just a link to this. This is the disease. I think this is for the drug, and I think this part is for maybe metabolic pathway, if I remember correctly. So there's a different ontologies, and we have many of them. These are just a sample of 3. So on that, so you can see that we have constructed very complex graphs, right? They're connected in some way, but by no means they are, they're uniform, or so we still need to actually build model to somehow make them, learn like a more unified representation of that, right? So because that graph is very heterogeneous, not only like the node can be of many, many different types, right? But also the edges of many, many different types. And also if you even look at the connectivities, some part is much denser than other part, and some part is very sparse. And the structure-wise, some places more like always hierarchical, and some place like a tree structure, and some other part maybe more cyclic, right? So we want, actually we spend quite a lot of effort on learning graph representations. So this is just one of the approach we're taking. So, and basically we want to learn the graph representations, and this is actually this is one of our early approach. So the beauty of graph representation is that basically actually in the end we have like vector representation, right? So we can do subsequent tasks in a more uniform space. Okay, so our later approach, basically you can see that because of all this, there's these ontologies, and there's this, the basic level is the basic patient level. So actually we do not, one big difference from our representation learning approach to others is that we don't try to map everything into one latent space, because we believe that would be, no matter what you do, there's some part of the graph you have to compromise a lot of things in order to map everything to the same space. Okay. Instead, we say, well, we want to map it to multiple intersecting space, because if you think about that, for ontologies, right? So it's more like a tree structure, right? And a tree structure that, which means that maybe like hyperbolic space is more suitable. Actually, there's a lot of people have demonstrated that. And so there's different geometric space we could use it for this. And then for the patient graph, right? So maybe it's a spherical space, or or even Euclidean space, it become more suitable. So you can see that, in another word, right? So basically we need geometric space of different curvature to represent this different type of topology. And then we want to automatically learn that. So, and this multiple spaces doesn't have to be independent, right? Do not touch each other, but they can intersect. Okay, so, and also you can see this nodes that actually is kind of at the intersection between, this, like from the patient to like maybe some kind of ontologies, right? They may reside on at the intersection of two, let's say, two geometric space. Okay, for example, if you have a spherical space and then you have another Euclidean space, and then if they intersect, it's kind of a ring, right? So I'm just giving you an example. It just a ring, so that whatever the node at the intersection of certain things all reside on that ring, just intuitively. But we turn out to be Euclidean space is not suitable for most of the things. Well, not the best for most of the things, even though a lot of people still using Euclidean space. So here basically just say we could map to multiple spaces and then to optimize the whole thing. So I know I'm running out of time. I just show a little bit of the diagram of like our unsupervised bias mitigation. So basically instead of just learning one encoder, right, we actually do a pair of encoders. And then we want this pair to be as orthogonal to each other as much. Okay, and such that, the first one the task is to really minimize the reconstruction error, right? To be honest to the data, which represent both the useful signals as well as the bias, as well as the noise, everything, right? So, but the second one, try to be, we'll try to disentangle them, so sort of like try to make them as orthogonal as possible to each other. And but here just to try to optimize on subsequent tasks, downstream tasks, try to optimize the performance of that. These two are not learned simultaneously, but not learned separately, but actually learned together. So that basically we wanted to optimize this reconstruction, optimize subsequent tasks, but kind of minimize the dependencies between E1 and E2. So that's our goal. And this can be used on dealing with text. This can also be used on, like I showed, that dealing with graphs. And also we have just to try to deal with there's a different patient with different amount of medical information available. So we try to using like attention model to try to basically overcome that. So to I know I don't have enough time, but try to mitigate that kind of bias. And so basically it's just going to be, we have a fairness loss here. We also have this the loss from the subsequent task. So we want to be able to minimize both loss simultaneously through multitask learning. Okay, so I just want to quickly summarize, and then fairness is very important issue to trustworthiness. So at UCLA, we have a big effort in trustworthy AI, and then we choose to use the graph as the unified representation, because this way we can have a lot of models to learn latent representation from that. And we want to leverage external knowledge to impute those missing data, and then to harmonize the heterogeneity in the data. So, and in the end, we want to do like fair representation learning to identify the remote bias. So I will stop here by seeing, okay, thank you for all my collaborators and students. So they did all the work. So I just give this presentation, and thank you very much. And if there's any question, I'm happy to answer.
Thank you very much for the awesome presentation. And yeah, like if anyone has any questions, please go ahead and ask.
Hello, Professor. Can you hear me?
Yes.
Yeah, okay. Hello, Professor. Thanks for a great talk. And I'm a PhD student in Illinois Institute of Technology, and I'm very interested in trustworthy learning. And could you have more comment on unsupervised bias mitigation and unsupervised bias mitigation? And could you have more comment on unsupervised bias mitigation?
More comments. So what type of code? So you mean here, right?
Yeah.
So
yeah.
Do you have any specific question?
I'm not sure how to do bias mitigation in an unsupervised way, maybe.
Yeah, because this is not supervised. This is not supervised because we don't need a human to go in to see, well, where the bias is.
Okay.
So you can think of like this E2 is just try to, the way is to make sure E2 only the essential information from the data to perform the task. All the non-essential ones, doesn't matter it's noise or bias, right? Or irrelevant information are gone because they are going to be part of E1, not part of E2, because that's why we want to entangle them, to make them as orthogonal to each other as possible. But of course, they probably won't be completely orthogonal to each other, but just make them as independent as possible to each other.
Okay. Okay, thank you.
Yeah, so one way to do that is like adversarial learning, but there's other ways of doing that. This is just a high level picture.
Okay, I see, thank you.
I see another question. Girma?
Yeah, thanks, Ramtin. Thanks, Professor. Great presentation. I'm Girma, actually from IBM Research Africa in Nairobi, Kenya. It's already midnight here. Actually, my work is in line with trustworthy AI in general. And detecting bias is often tricky because there are different bias, as you know. But my specific question would be, when you try to mitigate bias, how could you guarantee that you are not recreating another bias which was not there in the first place?
Well, that's a great question, right? So in our project, right, we first want to say, well, we want to make sure the final task, right, is performed with high quality, high performance, high accuracy, right? Whatever, if accuracy is the way to go, high accuracy, right? If the goal is try to maximize the survival rate, right, of something, right, based on the action we recommend, and then that's so basically the try to maximize the performance and only extract the essential information from that. For example, right, I wouldn't think like in all contexts, gender is a bias, right? In some contexts, gender is a bias, right? So it's like, the model prefer one gender or the other, only when actually gender is not a, essential factor, right? But for some of the texts, so if we study, I believe like, for example, diabetes, right? And then how the male patient and female patient respond to certain treatment may be quite different. It's just because in their body, the hormone system, just work somewhat differently, right? So in this case, we cannot just simply say, well, let's not look at gender. And we have to look at gender, right? We cannot just exclude that. So you can see what's a bias, what's not a bias, right? So it's like, it's not defined ahead of time, right? So in other words, we don't want to drop, critical information just because we think that may be part of bias, but we want to have the, the data speak out itself for itself. Yeah.
Yeah, and bias sometimes could be also a combination of different features, and a few
Right.
features could be fine by themselves, but a certain combination of features, for example, male with education level, for example, high school, older than 50 years old, these sort of combinations are usually tricky to identify and possibly mitigate as well. Do you have some experience in detecting and mitigating such complex looking bias in your work?
Well, we haven't done that explicitly, but what we did is that when we evaluate the performance on the final task, right, we want to make sure that we check, whether there's a specific, group of patients, right? So somehow the model performed poorly. But again, that's, if you only have one patient fit that profile, right? Like male, between 55 and 60, and then it's hard to determine, right? Whether that's bias or that's something else, right? Only when you have enough samples within, fitting certain profile, right? And the demographic profile, and then you see that systematically poor performance, let's say, for that, and then we can identify that.
Great, thanks.
Yeah.
All right, so if there is no more questions, so maybe we can move on to the next presentation. Thank you very much for your presentation, Professor Wang. And so our last topic is towards automatic detection of misinformation in online medical videos, presenting by Professor Rhoda Mihalce. Rhoda is a professor of computer science and engineering at the University of Michigan. Her research interests are in NLP, multimodal processing, and computational sciences in different areas. So unfortunately, Rhoda wasn't able to attend today's workshop, and she sent us a recorded video of her presentation. So let me see if I can play her great presentation for you. So let me know if you guys can hear this sound as well. So if you cannot hear it, so maybe I have to fix it.
Hello, everyone.
Right,
it's a
can you
great
guys
pleasure
hear it?
to be presenting today at this very timely workshop. And I would like to talk about work that we have been doing on the detection of misinformation in online medical videos in a joint collaboration between University of Michigan and the NYU Medical Center. As we know, there is a lot of misinformation out there, and what we are particularly focusing on in this work is the misinformation that appears around health data. There are a lot of health-related videos, and in fact, the statistics that we found shares the fact that in 2013, more than half of the US adults have looked online for health information. On the other side, looking at video content, there are close to 2 billion users using YouTube, and there are about 5 billion videos that are watched daily. Now, among all these videos, there is a fairly large fraction that talks about health information. So here are some examples, for instance. There is information that's being shared by MD Anderson Center on cancer symptoms that women should not ignore. And this is, for instance, a video that had close to 200,000 views over 5 months, or another video talking about upper GI endoscopy, which had more than 4 million views over 11 years. While ideally we would want to have only this kind of trustworthy health information, there is also a large amount of information that's also shared via videos, which is questionable. For instance, there are videos that will talk about the natural cure for prostate cancer, miracle cure, ways to heal naturally, and other treatments that are apparently 100% guaranteed through herbal treatments. So what we are dealing with in this work is the misinformation around medical conditions, and in particular, looking at the kind of misinformation that's being shared through video content. This is a major concern for public health because it can often lead to contradictions. It goes against established medical understanding, promotes only a subset of the facts, and it can often be misleading. Here is an example of a news being shared around how stage 4 cancer can be cured with baking soda. Now, the challenge with misinformation is not only that it's inaccurate, but in fact can lead to harm, as there is audience that is misled by the information being shared in these videos, may eventually follow the advice that's not informed medical advice, and it can overall lead to negative effects. As oftentimes people would not be able to reliably distinguish between trusted medical sources or untrusted sources that would still share medical information. One way to address misinformation is to have content moderators. This would be an ideal setting where we would have professional content moderators that would watch content and determine which content is trustworthy and which is not. However, this is not very feasible as a solution because it's costly and time-consuming. If we were to scale up beyond medical professional, then the challenge would be that not having the required medical background be in fact difficult to sometimes distinguish between what is trustworthy medical information or mistrusted sources. Ideally, we would want to have ways to do this automatically so we can scale it up. However, although there is growing work on misinformation detection, there is very little work on misinformation detection on healthcare data, and even less work on misinformation detection on healthcare data as expressed in multimodal content, such as videos. So what I'm talking about here is work that we've been doing on detecting misinformation around healthcare, and particularly focusing on prostate cancer, which is the second leading cause of cancer death. There are more than 500,000 prostate cancer related videos on YouTube, which some of them are trustworthy and some of them share the information that is not necessarily reliable and should not be followed. So in order to determine what are ways in which misinformation is being shared, we collected a data set of 250 videos, which were manually annotated as being misinformative or trustworthy by professional annotators, so annotators with a medical background. And on this data set, we can then identify what are some cues for linguistic, acoustic modalities, as well as user engagement that could lead to a model that can automatically detect the presence of misinformation. So I'm going to show a couple of examples just to make this more tangible and see which are some videos that express either misinformative or trustworthy information. So first, let me play an example of information being shared on prostate cancer.
I send all my family and friends an email it must have been 3 weeks ago, because today I've been here for 3 weeks, and said, wouldn't have been 3, would have been 2 weeks ago, and said, if any of you ever get cancer, come here first before you go to your doctor. Because here they use the stuff that's working for you, not the stuff that the government says they're going to pay for. Might cost you a couple of bucks, but if you want to walk out, come here. Come here. Guaranteed. Yeah. You sit there and you talk to everyone and you know.
Let me play another example, another video from our data.
When a man is newly diagnosed with prostate cancer, there are a few options he can choose from in terms of treatment. Which factors should he consider before deciding on treatment? The majority of men are diagnosed with what we call localized prostate cancer, meaning the cancer has not spread beyond the gland. While some of them might live forever and never die of their cancer, even without treatments.
So you've seen the two videos, and you can probably determine yourselves which is more likely to be a trustworthy source and which is more misinformative. However, what generally happens is that people have difficulty to make this distinction. And moreover, what we have found is that videos that are misinformative would often spread more widely. And so they would have a wider reach than the trustworthy medical videos.
When a man is...
So as I mentioned, the data set that we collected focusing on one disease, which is prostate cancer, includes 250 videos. It has wide coverage within this disease. So it covers risk factors, it covers prevention, screening, treatment, and so forth. And then it has various contributors. So there are media groups, there are professional organizations, there are doctors, patients, and so forth. And what we looked for when compiling this data set is that there are no animations or artificial voices. We only selected videos that use English as a language and a duration of less than 30 minutes. And then also we limited the videos to those that included at most 2 speakers. Almost half of our videos have 2 speakers and the remaining half have only 1 speaker. And these are videos that had about 10 million views as of April 2019. So an important part of our data collection was the annotation. We wanted to annotate these videos as being misinformative or trustworthy. For the misinformative annotation, we looked for those that were guideline discordant with respect to information, that rely heavily on anecdotal evidence, and also some that contain advertisement or content that was considered to be biased. We instead labeled as trustworthy those videos that were guideline concordant, included correct medical information, and were found to be unbiased. The annotation was done, as I mentioned previously, by experts, so medical professionals. Specifically, they were expert urologists, 92% within one inter-annotate agreement on a 10% random sample of the video. So we had fairly high agreement in the annotation. And for the annotation, we use a Likert scale on a 5-point with increasing levels of misinformation. So across the 250 videos, this is the distribution of labels. So again, going from 1 to 5, where 1 would be trustworthy, so there is no misinformation, and then there is increasing amount of misinformation all the way up to a level of 5, which is highly misinformative. Now, considering only a binary split, where all misinformative labels 2 and above would be grouped as into one category of misinformation, and then level 1, which is lack of misinformation, therefore trustworthy, would be the other class. So we have almost evenly balanced. So 132 videos were labeled as trustworthy, and the remaining 118 as misinformative. So here are two examples. You've seen the examples that I shared previously. In terms of language, here is an example of a misinformative content going like this: how I healed this prostate cancer naturally. I was diagnosed back in 2012. My urologist wanted to have me cut the prostate out. I was just freaked me out. I chose the alternative route. There is lots of research with a guy named Don Tolman. Do a Google search on him. He's amazing. Lots of raw fruit and vegetables, lots of water, fasting, sunshine, and so forth, and the miracle cure. And on the other side, if we look at the trustworthy example, it's talking about how some prostate cancers are low-grade, non-aggressive, and they may grow very, very slowly for many, many years and may require no treatment in that situation. We'll monitor the PCA over time, and that is called active surveillance. In patients who have a higher grade of tumor, we may offer them either some form of radiotherapy treatment or some form of surgery, and so on and so forth. So you see, we highlighted here some keywords which are more indicative of having this informal, non-professional speech talking about naturally miracle cure, no medical intervention, and so forth. Whereas on the other side, it's talking about low-grade, non-aggressive, higher grade of tumor, and so on. So we processed the videos. In the first step, we extracted viewer engagement metrics. As it turns out, they actually play a very important role. So we looked at how many views these videos had. Then we also extracted acoustic features from the speech. And from the transcription of the speech, we extracted linguistic features. So for viewer engagement, we obtained them through the official YouTube API. This includes number of views, thumbs up, and also creator type. For the acoustic information, we extracted raw acoustic features using the Open Ear Toolkit, which would also include some low-level features such as loudness, pitch, and male frequency substrate coefficients, MFCCs, and also some statistical manipulation of those, including max, median, and some other statistical metrics. And we also use 3 predefined sets that are typically used in emotion recognition: MO-base, MO-IS09, and MO-large, which are subsets of the acoustic features. For language, using the transcript of these videos, we extracted information about punctuation. So we first annotated with punctuation, and then we applied Stanford Core NLP. And this was applied on transcripts that were obtained either through YouTube, through the automatic captioning system, or for those videos that did not have this captioning service, we used the Google Cloud speech-to-text service. After this processing, we extracted several linguistic features using, including unigrams and bigrams. We measured the readability of the text, for instance, the number of words per sentence, and several readability metrics, which are typically measured as probability distribution with respect to standard reliability indices, for instance, distribution of words in different grade levels. We also extracted the LIWC features with 73 word classes, which are on psycholinguistic, defined on psycholinguistic basis. And then we also had parse trees from the syntactic annotation. And finally, all these features, we use a support vector machine since we did not have a lot of data, and it was very intensive in terms of data processing and annotation. So we were not able to create a very large data set that would be annotated for misinformation. Instead of using the now more common neural networks, we opted for a different machine learning model consisting of an SVM. And we did a 5-fold cross-validation, again, motivated by the same fact that we have relatively small data set, 250 videos. So we ran a cross-validation for evaluation. So here's what we found. I know it's a table with lots of results, but I think there are several interesting observations that we can make based on these. First off, the viewer engagement. So the number of views on a video turns out to be actually quite important. It's one of the best set of features. And this was an interesting find. It was a surprise for us. It turns out that misinformative videos are, in fact, getting a larger number of views than the trustworthy videos. And the number of views and likes, it's an indication of, can be an indication of misinformation. Then for the linguistic features, we found that the simple n-grams can lead to relatively good performance. Also, the use of syntax can be also useful. But all models do lead to some improvement overall. So there is some signal in all the representations on the linguistic side. And generally using all the linguistic features together, we got close to 73% F-score and 72% in terms of accuracy. And for the acoustic information, we got the best result with some of the emotion subsets of the acoustic features. They are, however, below what we can get with the linguistic information. So eventually the system that led to the best performance overall was one that combines viewer engagement with all the linguistic features, and also one of the emotion subsets of the acoustic features. So that gave us 74% accuracy, which is significantly better than baseline, a very simple baseline, which gets the majority as correct, which is our case would be labeling all the videos as trustworthy. So to conclude, we introduce the task of automatically classifying the misinformation in online medical videos through a data set of 250 videos that are focused on one disease, that of prostate cancer. The data set was annotated by experts, and we use a multimodal approach to classify misinformation for an overall accuracy of 74%, which I believe is promising in terms of how well we can detect misinformation in such content, in particular when specialized on the domain of healthcare. So in terms of potential future work, of course, there is always room for more data and improvement that way. I believe also the adoption of larger models can lead to improvements, and eventually also the extension to more modalities. For instance, in this work, we did not consider the visual modality. That is probably something that would be potentially useful. Similarly, we did not necessarily follow how the conversations would happen in the case of two speakers. So that's also a possible promising direction. And eventually where we hope we'll get is to this place where all misinformative videos will turn out as video unavailable, so we can detect them. And with that, thank you. I know I'm not available to take questions, but I would encourage you to reach out with questions by through the workshop organizers or by email. Thank you and enjoy the workshop. Hello, everyone.
All right, so thank you everyone for listening. I know that Professor Rada is not here, so if you guys have any questions, you can just ask me. I mean, like I can just email her later on, or maybe you can just email her yourself. And so I just want to, on behalf of all the organizers, I want to thank the speakers with the great talks, the authors for the great papers, and all the participants. And it was a great workshop with a lot of interesting presentations. I personally learned a lot from the presentations and different talks. So with that being said, I hope everyone enjoys the rest of the evening. And please check out the poster sessions. So there's, I think there are 2 poster sessions for poster 1. There's one more poster 1 session and the poster 2 sessions. And yeah, so they will be available on the website. And thank you again and take care. And by the way, yes, the recorded video will be available on the website in 1 or 2 days after I can upload it there.